Welcome to this comprehensive journey toward achieving your Palo Alto Network Systems Engineer Professional Strata certification. This course is designed to serve as your definitive roadmap for mastering the technical nuances required for success on the official exam. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to Palo Alto Networks in any way. All trademarks belong to their respective owners. In this opening chapter, we will establish the fundamental baseline necessary to navigate the complexities of enterprise-grade firewall architecture. You will gain a clear map of how our technical modules align with the official exam blueprints, ensuring every hour you spend studying contributes directly to your certification goals. We designed this curriculum specifically for pre-sales engineers who need to translate complex architectural concepts into tangible business outcomes. By the end of this course, you will not only be prepared for the exam format itself, but also for the real-world deployment challenges that define the systems engineer role. If you are aiming to validate your expertise in next-generation security and advance your career in the competitive network security landscape, you are in the right place. Let us begin this structured progression through the Strata landscape to ensure you possess the depth of knowledge demanded by today's enterprise environments. See you in the next lecture. Welcome to this exploration of the foundational architecture that defines our platform. In this chapter, we will demystify the internal workings of the next-generation firewall to provide you with the technical depth required for the PSE Strata certification. When we talk about the architecture of a Palo Alto Network's next-generation firewall, we are essentially discussing the intentional separation of responsibilities. Traditional firewalls often suffered from performance degradation because the same processor handled both management functions and packet forwarding. In our architecture, we maintain a hard distinction between the control plane and the data plane. The control plane is primarily responsible for management tasks, such as handling the graphical user interface, the command line interface, and log management. By isolating these processes, we ensure that administrative activities or heavy reporting tasks never steal resources from the critical path of traffic processing. This separation is foundational to the predictability of our security enforcement, regardless of the load on the management interface. The data plane, often referred to as the forwarding plane, is where the heavy lifting occurs. Unlike general-purpose CPUs found in common servers, our firewalls utilize specialized hardware components designed for high-performance networking. This typically involves a combination of dedicated processing chips that manage hardware-based tasks, such as flow lookup, encryption offloading, and standard packet switching. By delegating these functions to purpose-built hardware, the system can maintain high throughput and low latency, even under conditions that would force other firewalls to resort to software-based processing bottlenecks. This hardware-level optimization is the engine behind our ability to apply security policies to every packet without creating a performance penalty. Inside this data plane, we find a complex pipeline designed to handle various security engines efficiently. These engines are responsible for tasks such as signature matching, decryption, and threat prevention. By utilizing memory and specialized processors tailored for these functions, the device can execute security lookups in parallel rather than sequentially. For example, when a packet arrives, the system does not need to wait for a full signature check before beginning a decryption process if that path is required. This architecture allows the platform to perform deep packet inspection and classification simultaneously across the stream. Because the security engines are tightly integrated into the data plane, we successfully avoid the latency spikes that plagued the legacy modular firewalls of the past. It is important to understand that the distinction between software and hardware processing is not just about raw speed. It is about maintaining a deterministic environment where security policies are applied consistently, regardless of traffic volume or packet type. When you investigate hardware constraints versus software limitations, you're looking at the trade-off between the flexibility of updates, which are handled in software, and the performance requirements handled by the hardware logic. A well-designed firewall respects this balance by ensuring that even when a new security signature is deployed, the hardware layer continues to steer traffic at wire speed. By mastering this architectural breakdown, you move away from seeing the firewall as a black box and instead see it as a finely tuned system of decoupled high-speed components. Look forward to discussing how this architecture enables our unique traffic processing capabilities in our next session. Welcome to this exploration of the engine that fundamentally differentiates our platform from legacy security appliances. We will examine how the single-pass parallel processing engine achieves deep inspection without the performance penalties typical of traditional designs. In standard, legacy-style unified threat management systems, traffic often undergoes a serial processing chain. This means that a network packet is received and subsequently processed by discrete, separate software modules. First, the system might perform a routing lookup, then pass the packet to an application-level proxy, then to an antivirus scanner, and perhaps later to a separate URL filtering engine. This serial approach creates a massive latency bottleneck because each module must fully inspect or modify the packet before handing it off to the next stage in the pipeline. As you increase the security requirements, the packet buffer grows, and the processing time increases linearly, leading to the unpredictable latency that network engineers have fought against for years. The single-pass parallel processing, or SP3 architecture, was developed specifically to solve this serialization problem by rethinking where and how inspection happens in the memory space. Instead of a chain of independent modules, SP3 uses a unified, single-pass memory architecture where the packet is parsed and analyzed only once. As the packet enters the system, the hardware and software work in tandem to identify the application, the user, the content, and the security state simultaneously. Because the information is extracted into a single data structure, multiple security engines can act on that same data at the same time. There is no need for the packet to be queued or reprocessed between individual security functions, which effectively decouples security throughput from the total number of enabled features. If you consider how App ID functions within this ecosystem, you can see the efficiency gains in action. When a packet arrives, the engine immediately identifies the protocol and application, while simultaneously authenticating the user and evaluating the threat posture. Since the engine has already performed the heavy lifting of protocol decoding during the initial pass, the URL filtering, threat scanning, and policy enforcement modules do not need to perform their own separate protocol decode. They simply request the metadata that the system has already generated and cached within that single pass. This is a critical distinction, as it ensures that enabling deep packet inspection for a specific policy does not cause a sudden, massive drop in the interface throughput regardless of the total traffic volume. This parallel architecture is not just about raw speed. It is also about architectural consistency across the entire appliance. By using a single-pass approach, the system maintains a consistent state throughout the lifecycle of the communication flow. This architectural choice is why you rarely see the performance degradation on this platform that one might expect when enabling intensive features like SSL decryption alongside complex antivirus profiles. In a legacy proxy chain, enabling those two features would likely double the time a packet spends in the processing buffer, but in a parallelized stream, those processes are offloaded to run concurrently. It essentially treats the packet as a piece of data to be parsed comprehensively, rather than a sequence of obstacles to be cleared by various security checkpoints. In preparing for your professional certification, it is helpful to conceptualize this as a design pattern that favors efficient memory allocation and CPU scheduling. Traditional systems often rely on the CPU to perform extensive context switching to move packets between the different memory spaces used by various security modules. Because our engine operates on a single pass, it minimizes these context switches and keeps the packet data localized, which maximizes the performance of the underlying hardware buffers. It is this specific capability that allows these devices to handle high bandwidth throughput, even when all security subscriptions are active. Understanding this concept is foundational to explaining why the appliance remains stable under heavy load conditions, which is a frequent topic in architectural design scenarios. I will see you in the next lecture. Welcome back to our discussion on architecture. In this session, we will explore the foundational shift from perimeter-based security to the zero trust model within the Palo Alto Networks ecosystem. Zero trust is fundamentally a strategy, not a specific product or a single setting you toggle within your firewall. The core philosophy rests on the principle that implicit trust is a vulnerability. meaning we must shift our perspective to assume that no entity is safe simply by virtue of its location on the network. In a legacy environment, we often built a hard outer shell, treating everything inside the internal network as trusted. Palo Alto Networks helps us break this paradigm by moving the focus to the protect surface, which consists of the specific data, applications, assets, and services that are critical to your organization. By first identifying this protect surface, you create a baseline for establishing security policy that is rooted in business requirements rather than network topology. This approach demands that we move away from broad, zone-based trust toward granular, identity-aware controls that follow the data wherever it resides. To implement this effectively, we must first master the art of mapping our protect surface and understanding how traffic flows between these assets. You should begin by categorizing your resources and isolating them into micro-perimeters using the next-generation firewall as a segmentation gateway. This is where the mapping of implicit trust zones becomes essential, as you are essentially dismantling the flat network architecture that often allows lateral movement for adversaries. When a user, device, or application requests access to a resource, the firewall acts as the policy enforcement point, requiring continuous validation of the request context. This context includes user identity, application behavior, and device health, which must be inspected regardless of whether the traffic originates from the internal segment or an external connection. By forcing every flow through this validation framework, you ensure that security is decoupled from the physical location of the user. Configuring granular rules is the practical realization of these architectural design choices. Rather than broad directives that permit all traffic between segments based on IP and port, your policies should leverage the full stack of information available to the firewall. You are looking to define rules that explicitly allow only the necessary application-specific flows, effectively creating a whitelist model where everything else is denied by default. This requires a deep understanding of your traffic patterns to avoid disrupting legitimate business processes while maintaining a strict environment. Continuous verification is not just a one-time check at the start of a session, but a persistent enforcement mechanism that monitors the behavior of the session throughout its duration. If the nature of the application changes, or if the user context shifts, the firewall must be prepared to reevaluate the risk and enforce policy accordingly, ensuring that your protection remains dynamic. See you in the next lecture. Welcome back. Today we are exploring the different deployment modalities available within PAN-OS to integrate firewalls into various infrastructure topologies. Understanding how the appliance treats packets at the physical and link layers is essential for any engineer designing robust security architectures. In this chapter, we will examine the mechanics of tap mode, virtual wire, layer 2, and layer 3 deployment configurations. By the end, you will have a clear understanding of how each mode influences packet visibility, forwarding, and address handling, ensuring you can select the correct implementation for any given production environment. If you are looking to master the technical nuances of Palo Alto Networks deployments and confidently clear the Strata Systems Engineer Professional exam, this course is designed specifically for you. We strip away the marketing fluff and focus strictly on the operational mechanics that actually matter during high-stakes implementations. You will gain a deep understanding of not just how to toggle these configurations, but why specific topologies demand one mode over another based on your existing infrastructure. This is the definitive guide for engineers who need to deploy performant, secure, and architecturally sound networks without wasting time on trial and error. Tap mode represents the most passive deployment scenario where the firewall receives a copy of traffic via a switch span or mirror port. Since the firewall sits out of band and does not participate in the traffic flow, it cannot block packets or modify any header fields. This is an excellent choice for organizations wanting to gain visibility into their network traffic patterns, identify potential threats, or profile applications without altering current latency or network stability. You must ensure the chosen switch port provides a reliable copy of the traffic, often configured as an ingress-only mirror, to avoid performance degradations on the switch fabric itself. While this mode provides significant insight through the app ID and threat prevention engines, remember that it is entirely blind to encrypted traffic unless you transition to a more integrated deployment model. Relying solely on tap mode means accepting that you are purely an observer of the network, which is sufficient for auditing and discovery phases, but limiting for active enforcement. Virtual wire, or V-wire, acts like a transparent bump in the wire, allowing you to insert the firewall into an existing Layer 2 segment without requiring any changes to IP addressing or VLAN structures. When you connect two interfaces in a V-wire pair, the firewall essentially behaves like a transparent bridge that inspects, identifies, and enforces security policies on traffic as it passes through the pair. Because the firewall does not modify the MAC address or the destination IP, devices connected on either side remain blissfully unaware of the underlying security inspection taking place at the middle hop. You will find that this setup is particularly powerful for inline perimeter security, where you need to segment specific subnets or isolated data centers without re-architecting your entire routing topology. However, because vWire is transparent at layer 2, it does not participate in spanning tree convergence or ARP resolutions, which necessitates careful physical cabling design. It simplifies the implementation of zone-based security policies while maintaining the operational simplicity of a direct connection between your existing switches or routers. Layer 2 deployment mode transitions the firewall into a bridge-based architecture, where the device participates in switching protocols like spanning tree. In this configuration, you assign interfaces to specific VLANs, and the firewall performs MAC address learning on those segments to determine how to forward frames between zones. The primary advantage here is the ability to maintain consistent VLAN structures across the firewall while performing deep packet inspection on traffic traversing between different zones or even within the same broadcast domain. This setup is common in environments where you need to perform inter-VLAN routing security but cannot easily transition to Layer 3 gateway modifications. You must be mindful of the bridge group configuration as the firewall now acts as a functional part of the Ethernet fabric, meaning broadcast, unknown unicast, and multicast traffic will be processed according to your bridge forwarding tables. It effectively bridges the gap between simple transparent inspection and full routing-based security by adding granular control over frame forwarding via security policies. Layer 3 deployment is the standard routed mode where the firewall acts as a gateway for your subnets, performing full routing lookups for every packet. In this mode, you configure interfaces with IP addresses in their respective subnets, and the firewall uses its routing table or dynamic routing protocols to determine the path for ingress and egress traffic. Unlike the previously discussed modes, Layer 3 processing involves the decrementing of the TTL field and potential modifications to the Layer 2 header as the packet moves across subnets. This mode provides the highest level of control, enabling you to leverage the firewall not just for security policies, but also for path selection, policy-based routing, and innate services. It is the most robust way to integrate with wider network fabrics, supporting complex topologies that require redundant paths and high availability across routed segments. By acting as the Layer 3 hop, the firewall gains full control over the environment, allowing it to enforce security at the entry and exit points of isolated network segments while facilitating traffic flow through NAT and VPN gateways. See you in the next lecture. Welcome to this chapter on interface management, where we explore the fundamental building blocks of network connectivity on Palo Alto Networks platforms. We will cover the practical application of physical and logical interface configurations to ensure your environment is robust and secure. In this chapter, we will master the art of configuring interfaces so that they behave exactly as specified by your network design. We will examine how to define sub-interfaces for VLAN tagging, which is often the first step in segmenting traffic on a trunk link. You will learn to configure loopback interfaces, which are essential for management traffic and stable routing identities that persist independently of physical cable states. We will also delve into tunnel interfaces, which serve as the logical endpoints for secure point-to-point cryptographic connections. By the end of this module, you will be able to translate complex network requirements into functional configuration states on your firewall. Effective design requires a deep understanding of Layer 2 and Layer 3 parameters that define the behavior of an interface. When configuring your physical ports, it is vital to explicitly define speeds and duplex settings rather than relying on auto-negotiation, especially when connecting to older legacy switching hardware that might struggle with consistent state detection. You must also pay close attention to maximum transmission unit settings to prevent fragmenting traffic, particularly when dealing with encapsulated packets like those used in VPN tunnels. A common oversight is neglecting the link state drop behavior, which dictates how the firewall responds when a physical port loses connectivity. By configuring this accurately, you ensure that the firewall can rapidly converge and shift traffic to redundant links without waiting for timeout thresholds to trigger. Binding these interfaces to security zones is the mechanism by which the firewall enforces the principle of least privilege. An interface cannot process any traffic until it is assigned to a security zone, serving as the logical boundary that governs policy application. When you create a sub-interface or a tunnel interface, you must assign it to a distinct zone that reflects its trust level, even if logically it is part of the same physical hardware as another interface. Consider the scenario of a remote office connection where you utilize a tunnel interface. That tunnel must be assigned to an untrusted zone, while the local private network sits in a trusted zone. This logical separation is exactly what allows the firewall to inspect, filter, and secure the traffic traversing the cryptographic boundary with granular control. The precision of these configurations determines the overall visibility and integrity of your security posture. If your MTU settings are mismatched across a VPN path, you will encounter inexplicable connectivity issues where small packets pass while larger payloads are dropped, creating a nightmare for troubleshooting. Furthermore, using loopback interfaces for management traffic ensures that even if a physical port flaps or fails, your administration platform can still reach the firewall via a stable logical IP. These details might seem like mundane configuration chores, but they are the bedrock upon which advanced features like App ID and User ID operate. Providing a clean and well-structured interface layer allows the downstream security engines to function with minimal overhead and maximum predictability. See you in the next lecture. Welcome to this segment on advanced routing integration. We are going to explore how Pano's virtual routers handle complex networking environments and large-scale protocol exchanges. In this chapter, we will master the intricacies of configuring core networking protocols and routing services directly within Pano's virtual routers to facilitate seamless network integration. You will learn to implement robust static routing, dynamic OSPF, and BGP architectures, and complex route redistribution strategies that are essential for modern enterprise deployments. Investing time in this chapter is crucial, as routing proficiency is a core competency verified in the Strata PSE exam and is fundamental for building scalable firewall deployments. By the end of this module, you will possess the specialized knowledge required to manipulate metrics and manage multi-VR isolation instances effectively. When we approach routing within a Palo Alto Networks environment, the virtual router acts as the control plane for traffic forwarding. Unlike traditional routers, the virtual router in PAN-OS must consider security policy enforcement alongside reachability when making forwarding decisions. We often start by defining static routes, which provide deterministic paths for traffic, yet these remain insufficient for highly dynamic data center environments. To improve resilience, we implement path monitoring, where the firewall actively probes a destination IP to verify link availability. If the probe fails, the virtual router automatically removes the static route from the RIB, enabling seamless failover to an alternate path. This mechanism is critical when your firewall is positioned at the edge of multiple provider links, where BGP might not be strictly necessary for simple redundancy. Transitioning to dynamic routing requires a firm grasp of OSPF and BGP, as these protocols allow the firewall to adapt to topology changes without manual intervention. In an OSPF deployment, the firewall functions as a participant in your area architecture, sharing LSAs to build a consistent view of the network. We configure this through the virtual router's OSPF settings, where we define RID, areas, and interface authentication parameters to secure the neighborhood. BGP, on the other hand, is generally used for external peering, requiring careful attention to autonomous system numbers, route reflectors, and BGP path attributes. The complexity often arises when you need to exert control over these routes, which leads us directly into the necessity of route redistribution profiles. Route redistribution is the mechanism by which we bridge the gap between different routing domains or protocols. Without careful filtering, redistribution can easily lead to routing loops or performance degradation, which is why we employ redistribution profiles as a security layer. Within these profiles, We can match specific routes based on source protocol or community strings and manipulate metrics before injecting them into a different process. For example, when redistributing OSPF routes into BGP, you might need to adjust the MED or set a specific atomic aggregate to ensure the rest of your AS prefers the optimal entry point into your firewall cluster. This granularity ensures that the firewall remains an efficient transit point rather than a bottleneck in the path. The administrative distance parameter is your final safeguard when managing conflict between competing routing protocols that have learned the same prefix. By default, PAN-OS assigns specific weights to routes, but you can override these values to force the firewall to prefer a static route over a learned dynamic route. This approach is powerful, yet it is also dangerous if misconfigured, as it can hide routing loops or lead to black hole traffic. We must also consider multi-VR isolation, where we segregate traffic into separate virtual routing instances for multi-tenancy or distinct security zones. Because each VR maintains its own independent routing table, we must explicitly configure route leaking if we intend for traffic to traverse the boundaries between these isolated routing instances. Multicast routing completes our deep dive into advanced integration, requiring the configuration of PIM-SM to allow traffic from sources to reach interested receivers. In modern enterprise networks, multicast is often leveraged for video conferencing or financial data feeds, necessitating the firewall's ability to participate in the rendezvous point infrastructure. We must configure the virtual router to handle IGMP membership reports while ensuring that our security policies do not inadvertently block the underlying multicast stream delivery. By understanding the interaction between the multicast control plane and the security policy enforcement point, we ensure that streams are delivered only to authorized network segments. This holistic approach to routing allows for the deployment of a truly intelligent and adaptable edge infrastructure. I will see you in the next lecture. Welcome to this discussion on App ID, where we will examine the mechanics that allow the firewall to identify applications regardless of port or protocol. This chapter provides the critical foundation you need for the Strata certification by explaining how we move beyond traditional port-based security. In traditional network security, we relied heavily on port numbers and protocols to distinguish between legitimate business traffic and potential threats. This approach is fundamentally flawed in modern environments, because most applications now utilize dynamic port allocation or encapsulate their traffic within common ports, like 80 and 443. The App ID engine within the Palo Alto Network's firewall architecture functions differently by looking at the actual data stream rather than just the header information. When a packet first arrives at the interface, the engine performs initial protocol decoding to identify the underlying transport mechanism. This is not a simple lookup table, but an active process of normalizing traffic to strip away layers of abstraction and reveal the true payload. By focusing on the intrinsic characteristics of the traffic rather than the surface-level metadata, the firewall gains visibility into the application identity, regardless of how that data is packaged or how it traverses the network boundaries. Once the initial protocol is understood, the process moves into signature matching, which is the core of the profiling mechanism. The engine continuously inspects the incoming stream against a vast database of known application patterns that the firewall constantly updates. You can think of this as a highly optimized state machine that evaluates the byte sequences of an application handshake or the specific structures of a protocol exchange. If the traffic aligns with the specific signature defined for an application like Office 365 or a custom business tool, the firewall assigns that app ID to the session. This matching happens in the single-pass architecture, ensuring that performance remains predictable even when identifying thousands of concurrent applications. The efficiency of this process is paramount because the system must categorize the flow before it can apply any security policies, keeping the latency introduced by inspection to an absolute minimum while maintaining high fidelity. Not all traffic adheres to a static known signature, and this is where heuristics and behavioral analysis become essential components of the system. Some applications, particularly those designed to evade traditional security by masking their activity, will intentionally vary their payloads or utilize non-standard encryption methods to appear as generic traffic. The App ID engine employs heuristic techniques to analyze the behavior of the connection, such as packet size distribution, inter-arrival times, and sequence patterns. If the firewall sees a connection that lacks a specific signature but exhibits the structural symptoms of a known class of software, It can invoke advanced heuristics to categorize the session. This is particularly effective against evasive malware that attempts to tunnel through common protocols. By observing the flow's lifecycle, the firewall can flag suspicious behavior effectively and enforce security policies even when the application is technically unknown or encrypted. When the firewall encounters traffic that does not fall into any recognized category, it remains persistent in its efforts to categorize the stream. Unknown traffic is never ignored. Instead, it is handled according to the specific policy configured by the administrator. The engine treats this uncertainty as a data point, continually logging these flows so that the signatures can be refined. Palo Alto Networks maintains a sophisticated back-end infrastructure that processes these anonymous telemetry feeds to develop new signatures for emerging applications. These updates are pushed to your firewalls, ensuring that your security posture grows more robust over time as global traffic patterns shift. This constant evolution is the primary defense against modern masking techniques, allowing your security rules to remain effective even as application developers change their network behavior to hide activity from conventional inspection tools. See you in the next lecture. Welcome back. In this lecture, we are going to explore the mechanics behind engineering custom app ID definitions to manage traffic that remains unrecognized by the default Palo Alto content updates. When your organization relies on proprietary or in-house applications that don't conform to standard protocols, the default app ID signatures often fail to identify them correctly. This lack of identification forces the firewall to categorize such traffic as unknown TCP or unknown EDP, which creates significant challenges for security policy enforcement. By constructing custom app ID signatures, we provide the firewall with the specific context needed to classify this traffic accurately. This allows us to move away from permissive rules based solely on ports or generic categories, effectively enforcing the principle of least privilege. The process of engineering these identifiers is not just about making logs look better. It is about reclaiming control over the traffic traversing your infrastructure by ensuring that non-standard administrative business tools stop operating in the shadows of generic protocol labels. The foundation of any custom signature lies in identifying the unique characteristic patterns, or fingerprints, that distinguish your specific traffic from everything else. We begin by analyzing the application's transaction flow, which involves capturing packets to observe the initial handshake and subsequent data exchange sequences. When defining a custom app ID, you must specify the underlying transport protocol, typically TCP or UDP, and the associated destination ports used by the application, though it is often better to keep port definitions broad while keeping signature patterns highly specific. Within the Palo Alto interface, you can define these signatures based on fixed strings or using regular expression patterns to match specific headers or payload sequences. You should always aim for maximum specificity, as a broad signature risks matching legitimate protocol traffic to your custom application, which could lead to accidental policy bypasses or unexpected service interruptions. Context identifiers are the next critical layer, as they allow the firewall to look deeper into the stream to confirm the application identity beyond just the initial packet transmission. By setting criteria based on specific field values within the application protocol, you essentially harden the definition against packet injection or spoofing attempts. If you are dealing with a multi-stage application, you might need to chain multiple signatures together to ensure the entire session flow is correctly identified from start to finish. Once the signature is validated, you must consider the deployment carefully to avoid creating security blind spots. Often, this requires overriding predefined classifications if a custom application mimics the behavior of a known protocol that the firewall is already attempting to inspect. Applying these custom definitions correctly allows you to maintain granular security policies, ensuring that administrative traffic for your unique software is scrutinized with the same intensity as well-known enterprise protocols. See you in the next lecture. Welcome to the chapter on User ID, where we will bridge the gap between abstract network traffic and the tangible human identities within your organization. We will unpack how the firewall transforms ephemeral IP addresses into consistent, identity-driven security contexts. In an ideal network architecture, we would apply security policies based on roles and identities rather than the shifting sands of dynamic IP addressing. The architecture behind user ID is specifically engineered to solve this mapping problem by intercepting identity data at the source. Instead of relying solely on the network layer, the Palo Alto Network's firewall gains visibility into which human user sits behind a specific source IP address at any given moment. This allows us to move away from legacy rules that permit traffic for an entire subnet and instead enforce policies that follow a specific user regardless of their location on the wire. By integrating directly with enterprise directory services, the system creates a cohesive bridge between authenticated identity and granular network traffic control. To make this mapping function in a production environment, we deploy one or more user ID agents or use native integration methods to query identity stores like Microsoft Active Directory. These agents act as listeners that monitor high-privilege logs, such as security event logs on domain controllers, to detect authentication successes in real time. When a user authenticates, the directory server logs the event, and the user ID service captures this data, including the username, the source IP address, and the timestamp. This information is then pushed to the firewall where it populates the local user ID cache, effectively creating a real-time mapping table. Because these logs can be transient or noisy, the system employs sophisticated filtering to ensure only relevant login events contribute to the mapping database. Configuring directory group mapping is a critical step in finalizing this architecture, as raw usernames are rarely sufficient for dynamic policy enforcement. By querying the directory services for group memberships, the firewall can apply security rules to entire departments or functional segments, such as human resources or engineering, automatically. As users join or leave these groups in your central directory, the firewall syncs this information, typically via LDAP or Kerberos, ensuring that access levels remain consistent without manual policy updates. It is vital to consider the synchronization interval here, as there is always a trade-off between the overhead of frequent polling and the latency of identity information updates. An optimized configuration strikes the right balance to ensure that the firewall always has the most current view of who is accessing which resource. Maintaining these identity-to-IP mappings requires a robust back-end process that handles transitions cleanly. Users may switch machines, change their dynamic IP address through DHCP, or authenticate via different points of entry, all of which trigger updates to the mapping cache. The firewall manages these updates by prioritizing newer information and clearing stale mappings to prevent unauthorized access based on outdated credentials. If an IP address is released and then assigned to a new user, the system must process the new login event immediately to replace the old mapping record. This dynamic lifecycle management ensures that security assertions remain accurate, preventing scenarios where a new user inherits the permissions or restrictions of their predecessor's now defunct IP allocation. Reliable operation hinges on how we interface with the source directories, which often requires careful consideration of network topology and firewall placement. We often place agents in proximity to the authentication servers to reduce the latency of log scraping and prevent flooding the network with excessive query traffic. In highly distributed environments, multiple agents can feed mapping data to a centralized firewall or a set of firewalls, ensuring that the identity picture remains consistent across all branches. We must also consider the administrative overhead of managing these services and ensuring that the account used for directory queries has the necessary permissions without being an excessive security risk itself. Ultimately, this architecture is not just about logging. It is about building a foundation for zero trust, where identity is the primary unit of control. We'll see you in the next lecture. Welcome back. Today, we will examine the technical specifics of deploying user ID agents within your environment. We will cover the infrastructure requirements and configuration nuances necessary to map IP addresses to usernames effectively. To begin our implementation, we must distinguish between the Windows-based user ID agent and the agentless polling method. The Windows agent acts as a dedicated intermediary that scrapes security event logs from your Active Directory domain controllers to identify user sessions. From a design perspective, this reduces the load on the Palo Alto Network's firewall, as the actual heavy lifting of log parsing happens on the server side. You must install the agent on a member server within your domain, ensuring it has consistent network reachability to the domain controllers it needs to monitor. When configuring this, the service account assigned to the agent requires specific permissions to read the security event logs. Specifically, you should add this account to the distributed COM users group and the event log readers group on the targeted domain controllers. Without these granular overrides, the agent will fail to authenticate or read the logs, resulting in a breakdown of your identity-based security policies. If you opt for an agentless deployment, the firewall itself handles the polling of domain controllers via WMI or WinRM. While this simplifies your environment by removing the need for a separate Windows server, it introduces additional resource utilization on both the firewall and the Windows infrastructure. You must carefully calibrate the polling interval within the firewall's user ID configuration to balance data freshness against performance impact. In environments with a massive influx of logins, an overly aggressive polling interval can lead to latency in user-to-IP mapping updates. Additionally, you need to ensure that the registry auditing for logon events is correctly enabled on your domain controllers to provide the necessary data for the firewall to scrape. If your registry settings do not align with the required event categories, the firewall will simply see empty logs, rendering your policy enforcement visibility non-existent. Architecting for high availability requires a thoughtful approach to service accounts and network connectivity. You should never assign domain administrator privileges to the agent service account. Instead, adhere to the principle of least privilege by granting only the essential read-only rights to the event logs. For larger enterprises, relying on a single agent creates a single point of failure that could leave your firewall blind to new user associations. You can deploy multiple agents across different geographic sites or subnet groupings to ensure redundancy and distribute the workload. When doing so, you must configure the firewall to communicate with a primary agent and define failover priorities. Proper caching of credentials, when handled in adherence to organizational security policies, ensures that even during temporary network instability, the firewall maintains a degree of historical session data. Testing your configuration involves verifying the mapping visibility directly from the firewall command line or the web interface. You want to see accurate mappings of IP addresses, usernames, and the specific user groups to which these identities belong. If the firewall shows the IP address but fails to resolve a username, start by checking the connectivity to the domain controller and confirming the agent service status. Sometimes, firewall rules themselves prevent the agent from communicating with the Palo Alto platform. So verify that the required ports for user ID communication, such as 5007 by default, are permitted. By monitoring the logs on the agent itself, you can gain insight into potential parsing errors or permission denials that occur during the initial handshake. Consistent monitoring of these logs serves as your primary diagnostic mechanism when troubleshooting identity gaps in your security infrastructure. See you in the next installment. Welcome back to our technical journey through the Palo Alto Networks ecosystem. Today, we are exploring the methods for extending user identification beyond the standard Active Directory polling mechanisms. In many real-world environments, relying solely on an Active Directory agent is insufficient, either because of the presence of non-domain assets or the use of disparate authentication stores. When we talk about alternative user ID mapping methods, we are essentially discussing the enrichment of the firewall's mapping table from non-standard sources. One primary mechanism is the use of the XML API, which allows administrators to send custom mapping updates directly from an external management system or a script. This is particularly useful in environments where you might have a homegrown portal or a database that tracks user sessions and IP addresses in real time. By constructing a structured XML request, you can push user link events to the firewall, effectively treating your own application as an authoritative source of truth for identity. This programmatic approach gives you a level of granularity that automated agents sometimes lack, as it ties identity events directly to specific workflow triggers in your infrastructure. Another robust method involves leveraging syslog parsing, where the firewall acts as a listener for authentication-related logs generated by network devices. Think of a scenario where your wireless controllers or VPN concentrators generate specific log formats containing source IP addresses and associated usernames upon successful login. By configuring the user ID agent or the firewall directly to monitor these syslog streams, we can extract the identity information using predefined or custom regular expressions. The critical component here is the parsing engine, which must be perfectly aligned with the log format to ensure the firewall correctly maps the tuple of IP, user, and potentially the security group. This technique is invaluable for mapping guest networks or mobile device segments where traditional Windows-based polling logic simply does not apply. It transforms passive network logs into proactive identity intelligence, allowing your security policies to remain user-aware even at the edges of your infrastructure. When dealing with more traditional web-based authentication needs, the captive portal remains a standard, yet sophisticated, alternative for identity acquisition. This method intercepts unauthenticated traffic on a defined zone or interface and presents a login challenge to the user directly within their browser. The captive portal is often the last line of defense in identifying a user, especially when the device does not belong to the domain and lacks a persistent agent. We can configure the portal to authenticate against local databases, LDAP, Radius, or even SAML-based identity providers, thereby integrating seamlessly with modern cloud identity stacks. This ensures that even before a packet hits a protected internal resource, the firewall has established a verified association between a source IP and a specific identity. It is important to remember that this adds latency to the initial connection, so the implementation should be scoped to high-risk zones or specific guest segments to avoid impacting the user experience. Finally, we must discuss the integration of multi-factor authentication in these alternative workflows to ensure the integrity of the collected identities. Whether you're using a Radius implementation or a modern SAML assertion, the principle remains the same. We need a secondary guarantee that the user is who they claim to be. When the firewall challenges a user via a captive portal, linking that session to a SAML provider allows us to offload the authentication logic to an external platform that supports stronger proof of identity. This is particularly useful when mapping non-domain assets like Linux servers or contractor devices that operate outside of your internal Kerberos or NTLM flows. By requiring MFA at the point of network access, we create a stronger foundation for our security policies, ensuring that even if a device is compromised, the user session itself is validated. Implementing these alternative approaches requires careful planning of your trust boundaries, but it significantly elevates the accuracy of our identity-based security posture across diverse endpoint ecosystems. See you in the next lecture. Welcome to this deep dive into device ID, where we transition from identifying users to identifying the specific hardware accessing your network. In an environment where IoT devices and mobile endpoints outnumber traditional workstations, relying solely on IP addresses for security policy is a relic of the past. Device ID technology effectively changes this by allowing the Palo Alto Network's firewall to maintain a persistent identity for a device regardless of its network location or current IP assignment. This mechanism functions by gathering diverse attributes such as MAC addresses, vendor-specific information, hardware serial numbers, and observed traffic behavior patterns. By analyzing this combination of telemetry, the firewall constructs a unique fingerprint that survives DHCP lease changes or transitions between different subnets. You will find that this methodology is crucial for enforcing a zero-trust architecture, as it bridges the visibility gap between what a user is doing and what the hardware is actually capable of. The configuration process involves enabling device identification on specific interfaces, which then allows the firewall's single-pass parallel processing engine to extract identifying metadata from incoming packets. To generate these fingerprints, the firewall monitors passive data flows and utilizes various device profiling agents that report the specific characteristics of connected endpoints. You must configure profiling rules that dictate how the system categorizes these accumulated attributes into specific device types, such as printers, medical devices, or workstations. Once the firewall identifies a device, it maintains a stateful object representing that specific piece of hardware in its internal database. A significant benefit here is the ability to track device state transitions, which is particularly useful when a device's behavior deviates from its established baseline. By consuming this device-level data, you can create security policies that are not just user-aware, but device-aware, effectively preventing an unauthorized IoT device from masquerading as a trusted workstation on your secure internal segments. When we look at multi-dimensional access control, the real power of this deployment emerges when you synchronize device ID with existing user ID implementations. By combining these, you can write policies that only permit access to sensitive resources if the request originates from a known, managed hardware device operated by an authorized user account. This prevents, for instance, a valid user from accessing a sensitive finance server using a personal, unmanaged tablet that lacks the required security posture. You can utilize these device attributes directly within the source device field in your security policy rules to enforce granular microsegmentation. Since the firewall recognizes the device ID even if the user logs out or switches network ports, your security posture remains rigid and resistant to typical network layer spoofing attempts. The administrative overhead of managing these devices is simplified through visibility logs that detail exactly when a device was seen and what identity was associated with it at that moment. See you in the next lecture. Welcome to this module, where we deep dive into the core of rule-based traffic filtering in PAN-OS. We will focus on how to define, structure, and maintain security policy rules to ensure your firewall is both secure and manageable. Security policy rules in Palo Alto firewalls operate primarily as a top-down first-match system. When a packet enters the firewall, the device evaluates it against the rule base starting from the very first rule and continuing downward until a match occurs. The first rule that satisfies all configured criteria, source zone, destination zone, source address, destination address, application, service, and user identity, is the one that dictates the action. If no rule matches a packet, the implicit cleanup rule at the bottom of the policy stack performs a default deny. This sequential processing underlines why the order of your rules is arguably more critical than the rules themselves. A generic, broad rule placed too high in the stack will inadvertently capture traffic intended for more granular, specific rules further down. Understanding this order of operations is essential for avoiding unintended consequences in your traffic flow. The structural classification of security rules into universal, interzone, and intrazone types serves as a fundamental organizational mechanism. Universal rules apply to all traffic regardless of the zone transition, providing a baseline for common policies that must exist across the entire organization. Interzone rules act specifically upon traffic passing between two different security zones, which enforces the boundary control required in a zero-trust architecture. Intrazone rules govern traffic remaining within a single security zone, allowing for precise control over lateral communication between hosts sharing the same interface or VLAN. By distinguishing between these types, you can enforce specific security postures for different layers of your network. Failing to categorize these correctly often leads to overly permissive policies where lateral movement within a zone goes entirely unchecked. Maintaining distinct rules for these transitions helps keep your firewall configuration legible and auditable. Rule matching logic relies on a multi-dimensional tuple consisting of zones, addresses, users, applications, and services. While traditional firewalls focused heavily on IP addresses and ports, Palo Alto's App ID allows us to move toward application-based restrictions that are far more robust. When you define a rule, the firewall checks the source zone and destination zone first, followed by the source and destination IP addresses, then the associated user, the identified application, and finally, the requested service port. It is a common misconception that changing the port in a rule automatically changes the service being inspected, but the firewall requires the App ID to recognize the protocol signature. If your policy specifies SSH but the traffic is actually web browsing tunneled over port 22, the security policy will correctly identify the mismatch. By leveraging this granular matching, you narrow the attack surface significantly compared to port-based filtering. Rule shadowing, a phenomenon where a more general rule completely masks a more specific rule, remains a common architectural failure. This happens when a broad administrative rule, perhaps one allowing all traffic from a user segment, is positioned above a specific rule that intended to deny certain applications for that same segment. The firewall never reaches the lower, more restrictive rule because the upper rule has already satisfied the matching criteria. Detecting shadowing requires a disciplined approach to your firewall's rule-based audit, ensuring that broader policies always reside below more granular ones. You should perform regular reviews to identify these redundant or blocked rules, as they effectively render your security controls inactive. A clean rule base is not just about aesthetics. It is about guaranteeing that your security intent translates directly into functional reality. Optimizing your rule base is fundamentally about minimizing the complexity of the match logic while maintaining strict security postures. One strategy is to use dynamic address groups or tag-based memberships rather than static IP lists, which reduces the need for constant rule updates. You should also ensure that your application-based policies define specific applications, rather than using the any application placeholder, as any ignores the heavy lifting provided by the App ID engine. When you specify exact applications in your policy, you align the firewall's processing capabilities with the business needs of the network. Proper rule hygiene also dictates that you regularly remove unused rules, as stale policies increase the cognitive load for administrators and the potential for configuration errors. Consistent documentation of why each rule exists is the final piece of the optimization puzzle, transforming a complex configuration into an easily understood, enterprise-ready security framework. I will see you in the next lecture. Welcome back. Today, we are diving into the mechanisms of network address translation within the Palo Alto Networks landscape. Network address translation is a fundamental architectural component that allows us to bridge the communication gap between private, internal address spaces and the potentially untrusted external environment. When designing secure networks, we often find ourselves needing to hide internal topologies or conserve scarce public IP addresses, which is where NAT becomes indispensable in our policy design. Within the Palo Alto firewall environment, NAT is not just a routing utility, but an integral part of the policy enforcement framework that influences how the firewall handles traffic headers and session states. Understanding the distinction between source NAT, where we replace the internal source IP, and destination NAT, where we redirect incoming traffic to internal resources, is critical for achieving predictable traffic flows. We must observe that in these devices, the NAT policy is evaluated separately from the security policy, which creates a specific order of operations that every engineer must internalize. If we fail to account for this decoupling, we often find ourselves troubleshooting seemingly inexplicable connectivity issues that stem from incorrect zone associations. By correctly mapping traffic flows before they hit the security policy, we ensure that our rules remain clean and that our address transformation logic is applied consistently across all interfaces. In this session, we will dissect the NAT policy constructs to ensure that your configurations behave exactly as expected during critical production deployments. When we configure source NAT, we are essentially modifying the source IP address of the outgoing packet to represent an address in a different subnet, typically a public-facing address on the egress interface. Palo Alto firewalls handle this through dynamic IP and port translation, commonly known as PAT, which allows multiple internal hosts to share a single public IP address by assigning unique source ports to each session. This is the bedrock of outbound internet connectivity for most campus networks, providing scalability while maintaining the required security posture. During the configuration process, the firewall looks at the original packet, matches it against the NAT policy, and then updates the session flow with the new translated address. It is crucial to remember that the security policy itself will always evaluate the traffic based on the pre-NAT zone, meaning your rules should be written using the original, untranslated IP addresses. This specific design choice simplifies policy management significantly because administrators do not have to rewrite security rules every time an internal host changes its identity or when a service migrates to a different public IP. By decoupling the transformation logic from the intent-based security rules, we preserve the purity of our design and ensure that auditing remains a straightforward task for the entire infrastructure team. Destination NAT serves a different purpose, often being used to facilitate access to internal services from the public internet, such as hosting web servers or legacy applications that require specific inbound visibility. Static one-to-one mapping is perhaps the most common implementation here, where a public listener IP is mapped directly to a private backend server IP, ensuring a predictable and persistent entry point for external clients. When an incoming packet reaches the firewall, the device executes the destination NAT policy to replace the destination IP before the session is successfully routed toward the internal destination zone. Just like with source NAT, the session lookup occurs early enough that the security rule is consulted based on the original destination zone, such as the untrustworthy external buffer. This approach helps maintain tight security boundaries, allowing us to explicitly permit only the traffic that reaches the specific internal host we have defined in our static mapping. If we misconfigure these zones or the associated address objects, we risk failing the strict checks necessitated by the packet processing engine's default deny behavior for unknown traffic. Mastery of these destination translations requires a deep understanding of the underlying routing table and how the firewall resolves the next hop after the translation has been successfully applied to the ingress packet. The interaction between NAT policy logic and security policy lookup is often the most misunderstood portion of the firewall packet flow, leading to common errors in traffic engineering. Because the Palo Alto firewall uses a single-pass architecture, it evaluates the NAT policy to determine what the packet will look like, and then performs the security rule match, which uses the newly translated attributes if the NAT policy modifies the zone. Wait, let me clarify that. The security policy itself must be written using the post-NAT destination zone with the pre-NAT destination address. And this nuance is exactly where many configuration errors originate during complex deployments. We have to be meticulous when defining our address objects and zones, ensuring that they align with the expectations of the firewall's lookup process to avoid unintended traffic drops. When we observe the traffic flow in the logs, we see both the source and the translated information, which allows us to trace the packet's journey accurately across the wire and through the engine. Maintaining consistency here is not merely a preference, but a requirement for ensuring that our security posture remains immutable to changes in the IP structure. By internalizing this specific logic, you will be able to troubleshoot complex NAT scenarios with ease and design infrastructures that are both scalable and inherently secure. See you in the next session. Hello, and let's dive into the core concepts of SSL forward proxy decryption. This chapter focuses on restoring visibility to encrypted traffic flows. In a modern network, the vast majority of web traffic is encrypted using TLS, which creates a significant blind spot for security administrators if not properly addressed. If your firewall cannot inspect the contents of this traffic, it remains blind to threats hidden within secure sessions, effectively neutering the efficacy of your security profiles. When we talk about SSL forward proxy decryption, we are describing the process where the firewall acts as a man in the middle to terminate the client's SSL session and establish a parallel session with the destination server. By doing this, the firewall can inspect the decrypted payload, enforce security policies, and then re-encrypt the traffic before sending it to the destination. This mechanism is essential for enterprise security, as it allows features like URL filtering, antivirus, and file blocking to scan data that would otherwise be obscured. Without this, a malicious actor could easily bypass your defenses by simply wrapping their exploits in a standard HTTPS request. The architecture of this solution relies on the firewall having a chain of trust that the internal end-user devices respect and recognize. You must deploy a subordinate certificate authority certificate signed by your corporate internal root CA onto the firewall to perform this dynamic re-signing of certificates. When a user navigates to an external site like a banking portal, the firewall intercepts the initial handshake, retrieves the legitimate certificate from the server, and validates its authenticity. If the certificate is valid, the firewall generates a temporary cloned certificate on the fly, signed by your enterprise CA, and presents it to the user. From the perspective of the user's browser, the connection is encrypted, and the chain of trust leads back to the trusted corporate root CA pre-installed on the endpoint. This process must happen with negligible latency, which is why the underlying hardware's ability to handle SSL decryption at scale is a primary factor in choosing your firewall appliance. Configuring the firewall for this process requires careful attention to the cryptographic parameters you choose to support. You should enforce modern TLS versions, specifically TLS 1.2 or 1.3, to ensure that the connections are not susceptible to legacy vulnerabilities associated with older protocols like SSL 3.0 or TLS 1.0. Furthermore, managing the cipher suites is critical, as you want to prefer suites that offer perfect forward secrecy while disabling weaker options that could be exploited. Key sizes, such as using RSA 2048-bit or higher, are the standard expectation for secure communication today. Remember that decrypting traffic also introduces the need for managing the exclusion list, as many applications, such as high-security financial sites or health services, may use certificate pinning that will fail if the firewall attempts to present a forged certificate. Properly managing these exclusions ensures that your end users do not experience constant browser warnings or application connectivity failures while maintaining a high security posture. Protecting your endpoints ultimately depends on how well you manage this decryption policy within the context of your overall security architecture. When you create your decryption rules, you should be specific about the source zones, destination zones, and the services being targeted to avoid indiscriminately decrypting traffic that does not require inspection. This granular approach helps preserve firewall resources and reduces the risk of breaking applications that use proprietary or non-standard encryption methods. By centralizing the management of these certificates and the decryption policy, you gain full visibility into the threats that might reside in cloud-delivered applications. You are essentially bringing your internal visibility standards to the traffic that leaves your perimeter, enabling the threat prevention engine to act on the clear text data. This is a foundational skill for an engineer, as it allows you to defend against modern web-based threats effectively. I will see you in the next session. Welcome back. In this session, we will examine the architectural mechanics and operational requirements for implementing SSL inbound inspection on your next-generation firewall. When we discuss SSL inbound inspection, we are moving away from the paradigm where encrypted traffic acts as a blind spot for our security stack. In a standard deployment lacking this feature, an attacker can tunnel malicious payloads inside HTTPS requests directed toward your internal web servers, effectively bypassing your signature-based threat prevention mechanisms. By configuring the firewall to perform SSL inbound inspection, we position the security appliance as an intermediary broker that terminates the encrypted sessions destined for your internal infrastructure. This requires the firewall to possess the server's private key and public certificate, allowing it to perform the necessary cryptographic operations to peel back the TLS layer. Once the payload is decapsulated, the firewall can subject the original HTTP traffic to the full suite of security profiles, including vulnerability protection, antivirus, and anti-spyware checks. Only after this rigorous inspection process confirms the traffic is benign does the firewall re-encrypt the data and forward it to the final destination in your server farm. This process is functionally transparent to the end user, but it provides the visibility necessary to enforce a robust security posture for your publicly exposed web services. The deployment process begins with the secure importation of the internal server's certificate and private key into the firewall certificate store. It is important to note that you are effectively cloning the server's identity, which grants the firewall the authority to impersonate the destination server during the initial handshake with the external client. Once the certificate is imported, you must define a specific decryption policy that identifies the traffic flow based on the source zone, destination zone, and, most critically, the destination address of your web server. Within the decryption policy rule, you select the appropriate key/certificate pair that corresponds to the target server, establishing the bridge between the encrypted channel and the inspection engine. The firewall then intercepts the incoming client hello, negotiates the cipher suites, and manages the session state while maintaining the integrity of the transit data. This architecture necessitates that you treat the firewall certificate store with the highest level of administrative security, as the private key effectively becomes a critical asset that could compromise your infrastructure if improperly handled. Furthermore, you must ensure that your hardware resources are adequate to handle the additional compute overhead associated with high-frequency TLS decryption and re-encryption tasks at scale. From a workflow perspective, keeping the firewall synchronized with your internal PKI ensures that certificate renewals do not result in service outages. If a server certificate expires or is updated without corresponding synchronization on the firewall, the SSL handshake will fail, resulting in users receiving browser security warnings or dropped connections. It is also worth noting that inbound inspection is highly specific to the traffic you wish to protect, meaning you should explicitly define the scope of these policies rather than applying them globally to all traffic. By isolating the decryption policy to specific destination server objects, you minimize the performance impact and ensure that your security inspection is targeted precisely where the risk profile demands it. You will find that this methodology effectively aligns with the zero trust principle of inspecting all traffic, even when that traffic is wrapped in layers of encryption designed to obfuscate its true intent. When you combine this with rigorous threat prevention profiles, you gain the ability to drop malicious requests before they ever touch your backend infrastructure, which is a significant improvement over the blind trust model often found in legacy networks. See you in the next lecture. Welcome to this examination of decryption exclusions and the critical design patterns required to maintain operational stability while ensuring regulatory compliance. We will specifically focus on balancing the need for visibility against the requirements for privacy and application integrity. Decryption is fundamentally a double-edged sword that provides visibility into encrypted threats, yet introduces significant friction for sensitive traffic. When we talk about decryption exclusions, we are essentially defining a deliberate policy to bypass the SSL forward proxy for specific flows. This is not merely an optional feature, but a necessity dictated by legal, financial, and technical constraints. For instance, many jurisdictions maintain strict privacy mandates that prohibit the interception of traffic routed to financial institutions or healthcare portals. Furthermore, many modern applications utilize certificate pinning, where the client application strictly expects a specific public key and will terminate the connection instantly if it detects an intercepting proxy certificate. Implementing these exclusions requires a nuanced approach where we balance our security posture against these hard technical realities. The most effective way to handle these requirements is to leverage the predefined categories provided by the Palo Alto Network's Threat Intelligence Cloud. These category-based bypass lists allow you to automatically exclude entire classes of traffic, such as financial services or health and medicine, without manually managing thousands of individual URLs. This automation reduces the administrative burden and significantly decreases the likelihood of configuration drift as third-party services update their back-end infrastructure. However, relying solely on canned categories is rarely sufficient in an enterprise environment where custom internal applications or unique regional services represent a large portion of the traffic. You must be prepared to augment these automated lists with specific, custom URL-based or destination-based bypass entries to catch the edge cases that the broad categories miss. Beyond simple policy configuration, you must understand the mechanics of what happens when decryption fails. When a client initiates an SSL handshake with a site that we have chosen not to decrypt, our firewall must gracefully defer the process or handle the certificate exchange transparently. Problems often arise when the firewall attempts to intercept traffic that utilizes protocols or ciphers that are not fully supported, leading to bad certificate handshakes. To troubleshoot these scenarios, you must inspect the decryption logs and identify whether the failure stems from a protocol mismatch, a cipher negotiation issue, or a failure in the certificate revocation check. If the firewall cannot successfully query the certificate's revocation status via the certificate revocation list or the online certificate status protocol, it may default to a block action depending on your security profile rigor. Handling stubborn pinned applications represents the most difficult aspect of decryption management. Since these applications ship with preloaded certificates and refuse to trust third-party CAs, they will always trigger a security alert or connection reset when processed through a forward proxy. The only viable path forward for these applications is to explicitly identify the destination servers and include them in a formal decryption exclusion rule. You should maintain these exclusions with the same level of discipline applied to security policy rules, ensuring that your bypass list does not become an open door for exfiltrating malware that is clever enough to use known excluded destinations as a command and control channel. By monitoring the traffic patterns of your excluded entities, you can maintain visibility into those segments without infringing on the privacy or integrity of the sensitive applications involved. I look forward to our next session together. Welcome back to our discussion on fine-tuning your security infrastructure. In this session, we will focus on transitioning from broad, port-based firewall rules to precise, application-aware security policies using the Policy Optimizer. The primary challenge in managing legacy firewall configurations is the reliance on port-based rules, which often grant excessive access because they lack visibility into the actual applications traversing the network. Palo Alto Networks addresses this through the Policy Optimizer, a feature set that tracks application traffic patterns and identifies rules that allow traffic based on protocol rather than identity. By navigating to the Policies tab in the GUI, you can access the Policy Optimizer view, which categorizes rules into those that are strictly port-based and those that have already been converted to application-based policies. This tool provides a systematic approach to identifying where your security posture is overly permissive, allowing you to transition toward an App ID-centric model without the risks typically associated with manual reconfiguration. The process begins by reviewing the application usage graphs generated by the firewall, which reveal exactly what traffic is hitting your existing port-based rules. Instead of making assumptions about what applications your users require, you rely on concrete telemetry data that maps the specific applications detected during active sessions. Transforming a rule effectively requires a measured strategy to ensure that security is improved without disrupting legitimate business continuity. When you select a port-based rule within the optimizer, the interface displays a list of applications identified within that rule's current scope, grouped by those that are seen and those that are partially identified. You should prioritize the transition of rules with the highest traffic volume, or those that bridge critical network segments to maximize your return on effort. You can then use the policy clone feature to create a new application-based rule while keeping the legacy port-based rule as a fallback, which is an excellent way to safely validate changes. As you move the identified applications into the service column of the new policy, the system continuously monitors for any traffic that might still be falling through to the legacy rule. Once you have verified that the new rule is successfully handling all intended traffic, you can disable the legacy rule and monitor the environment for a period of time before eventually deleting it. This iterative approach minimizes operational impact and ensures that your firewall remains a surgical tool rather than a blunt instrument. Maintaining a clean security policy is not just about conversion. It is equally about auditing unused and stale configurations that accumulate over time. Rules that have seen no traffic hits for an extended period, often referred to as shadowed or redundant rules, can introduce significant security risks and obscure the intent of your overall configuration. The policy optimizer provides clear visibility into last used timestamps, allowing administrators to definitively identify candidates for archival or removal. Before purging these rules, however, it is standard practice to export them as part of a configuration backup, ensuring that you can revert if an unusual or infrequent business process suddenly requires a previously unused rule. Auditing also extends to security posture changes. You should track when policies were modified and what specific objects were updated to ensure compliance with organizational change management policies. By cleaning up these stale configurations, you reduce the complexity of the security database, improve lookup efficiency, and make future troubleshooting tasks significantly more manageable. Effective policy management requires that you view the firewall as a dynamic entity that matures alongside your organization's technical needs. When you consistently apply these auditing techniques and leverage automated translation tools, you ensure that your security environment remains predictable and aligned with the principle of least privilege. Always remember that the goal of moving from port-based to application-based policies is to reduce the attack surface by ensuring that only authorized, verified traffic patterns are permitted through your infrastructure. While the initial workload of transitioning legacy rules can be substantial, the resulting increase in security, granularity, and visibility is well worth the effort for any professional engineer. By keeping the configuration small, relevant, and audited, you simplify the path toward comprehensive network visibility. See you in the next lecture. Welcome back to the course. In this chapter, we explore how to leverage antivirus and anti-spyware profiles to inspect Layer 7 payload streams and fortify your network perimeter. Security profiles are the components that transform a firewall from a simple gatekeeper into an active participant in your defense in depth strategy by performing deep packet inspection on allowed traffic. When you construct an antivirus profile, you are essentially defining the parameters for the engine to scan file transfers across protocols like HTTP, FTP, SMB, and IMAP. The system decomposes these streams, reassembles files, and compares them against the known threat database provided by Palo Alto Networks. It is important to remember that these profiles only function if the traffic is permitted by a security policy. The security profile itself is merely the inspection mechanism applied to the flow. You must associate these profiles with specific security policy rules to ensure that the inspection happens where it is most relevant to your business needs and risk profile. By tailoring the action behaviors, such as alert, drop, reset, or block, you can strike a balance between aggressive security posture and operational uptime. Anti-spyware profiles handle a different layer of the threat landscape by focusing on patterns and behaviors associated with malicious activity, command and control communications, and DNS-based threats. While antivirus focuses on the content of a file, anti-spyware profiles monitor the intent and the destination of the traffic patterns traversing your network interfaces. You can configure these profiles to identify and block traffic that matches specific signatures associated with spyware, Trojans, and even unauthorized tunneling protocols. For instance, if you detect an internal host attempting to communicate with a known malicious pattern, you might choose to drop the connection or simply reset the state to terminate the session without notifying the client. This granular control is essential when dealing with compromised assets that may be attempting to leak information or pull down secondary payloads from external sources. Effective configuration requires a deep understanding of your own internal traffic baseline, so you do not inadvertently trigger false positives that disrupt legitimate business processes. One of the most critical aspects of modern anti-spyware configuration is the integration of DNS security, which addresses the reality that attackers frequently use the domain name system to facilitate their illicit activities. By enabling DNS sinkholing within an anti-spyware profile, you redirect requests from malicious domains back to a controlled, non-routable IP address owned by your organization. This is particularly effective against fast-flux DNS techniques, where attackers rapidly change the IP addresses associated with a domain name to evade static blacklists. When a client attempts to resolve such a domain, the firewall intercepts the request and provides the sinkhole address, effectively isolating the compromised internal asset from the malicious infrastructure. This action also generates a specific log entry, which is invaluable for your security operations team as they search for the source of the infection and define the scope of the impact. Furthermore, these mechanisms can detect data exfiltration attempts, as the firewall can identify unusual DNS query patterns that suggest a covert channel being used to tunnel stolen data out of your environment. The precision with which you apply these profiles determines the overall effectiveness of your security policy architecture. Do not fall into the trap of applying a one-size-fits-all profile to every rule in your configuration, as this can introduce latency and complexity without providing additional security value where it is not needed. For highly sensitive segments, such as financial databases or human resources platforms, you should maintain more restrictive profiles that drop traffic upon the slightest hint of anomalous activity. Conversely, for developer segments that might legitimately access external testing repositories, you might opt for a more permissive profile that alerts on suspicious signatures rather than blocking them outright. You should also constantly audit your signature categories to ensure that you are focusing on the threats relevant to your industry. By refining these actions at the signature category level, you streamline the processing burden on the hardware while maintaining a robust barrier against both known and emerging threats. Catch you in the next lesson. Welcome back to the course, where we turn our attention toward the practical engineering of vulnerability protection profiles. In this session, we will explore how to shield your enterprise assets from exploits and prevent lateral movement through granular policy control. Vulnerability protection profiles act as a critical gatekeeper for traffic traversing your network, specifically targeting known software exploits that aim to compromise client machines or enterprise servers. Unlike antivirus signatures that focus on file-based threats, vulnerability signatures inspect the protocol stream for malformed traffic or attempts to execute unauthorized commands on vulnerable systems. When you configure these profiles, you are essentially defining a rigorous heuristic against which all packets are measured. It is crucial to understand that these signatures are grouped by severity levels, allowing you to prioritize the mitigation of critical exploits over lower-risk informational alerts. By applying these profiles to your security policies, you create a dedicated layer of defense that operates independently of the application layer, ensuring that even if an application is permitted, its underlying traffic remains clean of exploitation attempts. To manage these protections effectively, engineers must utilize host-based exceptions when a signature creates a false positive or interferes with legacy application traffic. Creating an exception involves identifying the unique signature ID and determining whether to drop, reset, or bypass the traffic for specific destination or source IP addresses. This granular control is essential because a global block rule that works for the majority of the network could inadvertently break a critical, albeit unpatched, internal server. You should always aim for the most restrictive profile possible, but never at the cost of service availability. When you apply exceptions, maintain documentation regarding why a specific host or application was excluded from the standard policy. This practice is vital for maintaining a clean audit trail and ensuring that security overrides do not become permanent gaps in your defensive posture. Beyond simple packet inspection, the modern threat environment demands protection against brute force attacks and lateral movement, which we manage through threshold-based block rules. These rules detect anomalies in traffic volume or request frequency, allowing the firewall to automatically drop traffic from a source that demonstrates malicious patterns. For instance, if a workstation attempts hundreds of unauthorized connections against a database server within a few seconds, the threshold trigger will identify this as a potential credential stuffing or scanning attack. By setting these triggers appropriately, you can effectively silence and compromised host before it can map your internal network or reach high-value targets. This capability is instrumental in stopping lateral movement, which is the primary vector for ransomware propagation within internal segments. Integrating packet capture mechanisms into your vulnerability protection strategy provides the empirical evidence required for deep technical investigations. When a threat signature is triggered, the profile can be configured to take a snapshot of the offending transaction, which is stored on the firewall for forensic analysis. This feature is particularly useful when you need to verify whether a block action was accurate or to understand the specific payload that triggered an alarm. In a production environment, you should reserve deep packet captures for specific high-risk zones to avoid saturating storage resources and impacting firewall performance. When combined with threat logs, these packet captures allow you to reconstruct the attack lifecycle, providing visibility into the exact method used by an adversary to gain a foothold on an internal asset. Focus on integrating these profiles tightly with your existing security policy rules to ensure that every segment of your network perimeter is covered. You achieve the best results by applying a balanced profile that accounts for both the sensitivity of the internal infrastructure and the nature of the traffic it consumes. Remember that vulnerability protection is just one component of a broader security strategy, requiring consistent tuning and vigilance as new exploits emerge. By systematically organizing your signatures and monitoring threshold triggers, you create a robust barrier that forces attackers to abandon their efforts rather than succeed. Use the insight provided by threat logs to adjust your profiles whenever new patterns of malicious behavior emerge within your environment. See you in the next lecture. Welcome back. Let us explore the mechanics of advanced URL filtering within the Palo Alto Networks ecosystem. Managing web traffic is no longer a matter of maintaining simple blacklists of known malicious domains. The advanced URL filtering module shifts the paradigm from static database lookups to inline, cloud-delivered security that evaluates web content in real time. When a user requests a URL, the firewall does not just resolve a reputation score. It performs a deep, predictive analysis of the page before the content even renders in the browser. This approach is fundamental because it counters modern attacks that morph their infrastructure faster than traditional security updates could ever propagate. You are building a policy architecture that relies on automated detection rather than human intervention to keep up with the scale of the internet. To implement this effectively, you must understand how to manage custom URL categories alongside predefined classifications. While predefined categories allow for broad administration of common web types, your specific environment likely hosts unique applications or internal portals that require granular control. You can create custom URL categories by grouping specific domains or regex patterns, assigning them a unique stance within your security policy. Once these categories are defined, you must map them to URL filtering profiles where you designate specific actions like alert, block, continue, or override. Customizing the user response page is equally vital, as it transforms a generic browser error into a clear communication of company policy and expectations for your users. A significant component of this module is the prevention of credential phishing, which exploits human trust rather than technical vulnerabilities. The advanced URL filtering subscription enables the firewall to inspect the submission of credentials to websites, identifying potential phishing attempts based on real-time analysis of the site structure. When a user attempts to enter credentials into a site that behaves like a login page but lacks a verified reputation, the engine intervenes, You should configure these settings to ensure that sensitive company credentials never leave your perimeter to reach unauthorized third-party services. This automation is a critical defense against attackers attempting to harvest corporate logins through sophisticated social engineering. Beyond protection, you have the capability to enforce safe search policies and granularly inspect HTTP headers. Modern search engines provide mechanisms to strip explicit results from queries when a specific HTTP header is present in the traffic. By configuring your URL filtering profile to append or inspect these headers, you ensure that search requests originating from your network adhere to organizational content standards. Furthermore, controlling access to cloud services often requires inspecting the HTTP header to identify specific tenants, preventing users from logging into personal accounts while allowing access to corporate instances of software as a service providers. This level of control represents the transition from broad network blocking to intent-based traffic management. See you in the next lecture. Welcome to this section on wildfire, where we will examine the mechanics that allow Palo Alto networks to identify and neutralize sophisticated threats in real time. By mastering these integration techniques, you will gain the ability to leverage cloud-based intelligence to effectively protect your network from unknown malware. Wildfire is fundamentally a global cloud-based malware analysis platform designed to address the challenges posed by polymorphic malware and zero-day exploits. When an unknown file traverses your Palo Alto network's firewall, the system evaluates it against existing threat intelligence and security profiles. If the file is deemed suspicious or simply unknown, it is forwarded to the Wildfire cloud for a rigorous, multi-stage analysis process. This mechanism ensures that even files that have never been seen before in the wild are subjected to deep inspection before they can potentially compromise your infrastructure. Engineers must configure specific file forwarding rules to automate this process, ensuring that binaries, scripts, and archives are pushed to the cloud consistently without hindering user experience. The analysis process begins with static analysis, where the system inspects the file structure and metadata without executing the code. This is significantly faster and allows the system to identify fingerprints associated with known malicious authors or packaging tools. Following this, machine learning models are applied to detect subtle behavioral characteristics that are often invisible to signature-based detection mechanisms. These models are constantly refined by the massive amount of data ingested from the global Palo Alto network's footprint, allowing the system to learn from threats encountered anywhere in the world. By the time a file reaches this stage, the platform has already gained a significant amount of context about potential malicious intent. When deeper inspection is required, the file is subjected to dynamic execution within a bare metal hypervisor. Unlike traditional virtual machines, which some malware can detect and evade, a bare metal hypervisor provides a representative hardware environment that renders the malicious payload unaware of its sandbox status. This allows zero-click exploits and sophisticated evasive malware to reveal their true nature by attempting to communicate with command and control servers or modify system files. If the file is confirmed to be malicious, Wildfire generates a signature and creates a behavioral report, which is then distributed to all subscribed platforms. This closed-loop system ensures that a threat discovered on one network is effectively blocked on every other network globally within minutes. To set this up, an engineer must navigate to the Device tab and access the setup for Wildfire, ensuring the appropriate service region is selected for compliance and performance. Forwarding rules are then defined within the security profile, specifically in the file blocking and Wildfire analysis sections. You choose which file types, such as portable executable files, Office documents containing macros, or compressed archives, are to be inspected. It is essential to balance the need for security with the constraints of network latency and available bandwidth, particularly when dealing with large volumes of traffic. Once these rules are active, the firewall manages the connection to the Wildfire backend, handling the transport layer security through the management interface. As the administrator, you should also consider whether to enable the forwarding of private, company-specific files. While this can provide a degree of visibility into custom code being used across your organization, it does involve sending potentially sensitive internal traffic to a third-party cloud. The analysis results are logged in the Monitor tab, providing a transparent view of every file that was sent for analysis and its subsequent verdict. This log integration is critical for maintaining an audit trail and for understanding the scope of potential incidents when a malicious file is successfully neutralized. By understanding these mechanics, you position yourself to configure more resilient security policies that mitigate the risks associated with evolving cyber threats at the edge. I will see you in the next part of our technical deep dive. Welcome back. We are now diving into threat log analysis and reporting to understand how to turn raw security profile data into actionable incident intelligence. When we analyze threat logs, we aren't just looking at a list of events. We are reconstructing a timeline of activity within our network fabric. The PAN-OS log viewer acts as our primary interface for this interrogation, and mastering its filter syntax is essential for anyone aiming to be a proficient systems engineer. You might find yourself investigating a sudden spike in traffic, which requires you to look beyond the top-level alert. By isolating specific threat IDs or source IP addresses, you can quickly group related entries that appear disparate at first glance. This is where the single-pass nature of the firewall provides immense value, as it labels traffic with consistent metadata across all security profile matches. Understanding how to correlate these fields allows you to see the true scope of a compromise rather than just a siloed event entry. Analyzing wildfire submission logs is a distinct process that requires an understanding of how file-based threats are evaluated in the cloud. When a file triggers a submission, the log entry provides a hash of the file along with the verdict status, which helps in identifying zero-day threats. If you encounter a malicious verdict, you must trace the original source IP and the application ID that facilitated the file delivery. This process often involves looking at packet capture snippets associated with the file transfer to determine if the payload was encrypted or if it originated from a known malicious domain. You aren't just reading logs. You are acting as a forensic investigator who needs to connect the signature-based alert to the actual network flow. This verification is vital for ensuring that your current security policy is actually blocking the intended traffic rather than just logging it for retrospective review. Behavioral threat descriptors are another critical component when deciphering sophisticated attacks that evade traditional signature matching. Within the threat log, you will often find indicators related to command and control communication, such as unusual outbound API calls or beacons to suspicious infrastructure. These behavioral patterns are often documented in the threat details section of the log entry, providing context on why a specific traffic pattern reached a certain severity score. As an engineer, your objective is to evaluate these severity scores, informational, low, medium, high, or critical, against your enterprise environment's risk appetite. A high severity score on a server segment carries significantly different implications than the same score on a guest wireless network. You must normalize these ratings to determine which events demand immediate remediation versus those that can be addressed during routine maintenance intervals. Tracking remediation events is the final piece of this puzzle, ensuring that the life cycle of a threat is effectively closed. Once you have identified the threat source and assessed its severity, the PAN-OS system provides ways to track the follow-up actions taken, such as IP address blocking or custom application overrides. It is a good practice to verify subsequent log entries to ensure that a threat actor has not shifted their methodology or target vector following your initial remediation step. This is essentially a continuous feedback loop where your log analysis informs your policy adjustments, and those adjustments generate new, cleaner log data. Maintaining this cycle is what prevents a successful initial breach from evolving into a protracted security incident. Your role depends on translating these cryptic log lines into a coherent narrative of defense that supports the broader organizational security architecture. See you in the next session. Welcome to our exploration of file blocking and denial of service protection, where we transition from identifying traffic to actively hardening our network perimeter. In this chapter, we will master the mechanics of granular file control and volumetric flood mitigation. When we approach the challenge of data exfiltration and malware delivery, we must recognize that the application layer provides the context, but the file blocking profile provides the enforcement. A Palo Alto Networks firewall does not simply look at a stream of bytes. It deconstructs the encapsulated file within sessions like HTTP, FTP, or SMTP. By configuring a file blocking profile, you assign specific actions, alert, block, or continue, to various file types based on their extensions. Imagine a scenario where you want to prevent users from uploading executable files or scripts to external cloud storage while allowing standard documents like PDFs. You create a profile that identifies the file type through the firewall's signature database, ensuring that even if a user renames an .exe file to TXT, the content-based inspection engine detects the actual file signature. This level of granular control is essential for preventing the initial stage of many ransomware attacks, where malicious payloads are often delivered through common protocol vectors. Beyond mere file inspection, we must address the availability of our security infrastructure, which brings us to denial of service, DOS protection. These attacks aim to exhaust the firewall's hardware resources, specifically the control plane or the data plane, by flooding it with illegitimate traffic. We implement DOS protection profiles to establish baseline behavior and define threshold triggers for various protocols. When we configure a profile, we focus heavily on SYN floods, which attempt to exhaust the session table by initiating TCP handshakes that are never completed. By setting aggressive thresholds for these connections, the firewall can drop suspicious traffic before it consumes the session resources required for legitimate business traffic. These profiles operate on a per-zone or aggregate basis, allowing us to distinguish between normal traffic spikes and an actual concerted effort to degrade service availability. To build a robust defense, you must also understand the distinction between DOS protection profiles and zone protection profiles. While a DOS profile is attached directly to security policies to manage specific traffic flows, zone protection profiles are applied at the ingress interface level to act as a first line of defense. A zone protection profile is your mechanism for mitigating flood attacks based on protocols like UDP, ICMP, and non-IP traffic types. You should establish flood thresholds that trigger when packets per second exceed a value that would typically signal an anomaly for your environment. When these thresholds are breached, the firewall enters a state of restricted processing, often utilizing random early detection or simply dropping the offending packets. It is a balancing act. Setting thresholds too low will block legitimate traffic, while setting them too high leaves the infrastructure vulnerable to volumetric exhaustion. The interaction between these profiles and the single-pass parallel processing SP3 architecture is what makes this defense effective. Since the firewall inspects packets for DOS triggers and file signatures simultaneously with other security checks, there is no significant latency penalty for stacking these protections. You should always link your file blocking configuration to the specific needs of the business unit or the application profile being used. For instance, an email gateway policy will likely have much stricter file blocking rules than a general web access policy for a branch office. By carefully mapping these profiles to our security policies, we ensure that we are not performing redundant or overly aggressive inspection that could hinder valid business workflows. Ultimately, the objective is to create a deterministic environment where the firewall reliably identifies the intent of every file transmission while shielding its own processing power from exogenous stress. See you in the next session. Welcome back. In this chapter, we explore the design principles and configuration requirements for deploying secure IPsec site-to-site VPN tunnels across public routing infrastructures. When we talk about IPsec site-to-site VPNs, we are essentially building an encrypted overlay network that leverages the public internet as a transport mechanism. The primary goal is to ensure that data originating from a private internal network reaches a remote site without being exposed or intercepted. This process relies on a two-phase negotiation structure, often referred to as the IK gateway phase and the IPsec tunnel phase. In the first phase, or IK phase 1, the two gateways authenticate each other and establish a secure management channel. This is where we define cryptographic profiles, focusing on the integrity and privacy of the control plane by selecting appropriate encryption algorithms like AES-256 and hash functions like SHA-256 or SHA-512. It is critical to align the Diffie-Hellman group settings on both ends, as a mismatch here will prevent the security association from ever forming, effectively halting the tunnel initialization process before it begins. Once the control plane identity is verified, we move to the IPsec tunnel phase, which handles the actual carriage of user traffic. Here, we define a crypto profile that determines how the data packets are encapsulated and protected inside the transport layer. You must decide whether to use authentication header or, more commonly, encapsulating security payload, as the latter provides the necessary encryption functionality for modern security standards. We also bind these tunnels to a virtual router, which acts as the logical interface through which traffic is routed toward the remote peer. In environments using legacy gear that does not support route-based VPNs, you will encounter the necessity of configuring proxy IDs. These IDs serve as a traffic selector, explicitly defining the specific internal source and destination subnets that are permitted to traverse the tunnel, ensuring that both sides of the connection agree on the scope of the encrypted traffic. Beyond the initial cryptographic handshake, maintaining the availability of the tunnel is a distinct operational challenge that engineers must address. If the underlying internet path fluctuates or experiences latency, the tunnel might remain in an established state while being incapable of carrying traffic efficiently. To mitigate this, we implement path monitoring, which uses periodic pings or heartbeats to verify the reachability of the remote peer through the tunnel interface. By assigning a threshold for these monitoring packets, the firewall can determine when a path is failing and automatically trigger a switch to a redundant failover circuit. This design pattern removes the need for manual intervention during transient provider outages and keeps your connectivity predictable. It is a pragmatic approach that separates link state monitoring from actual traffic processing, providing a robust abstraction for your site-to-site connectivity requirements. When designing these architectures, you should always treat the tunnel interface as just another interface on your virtual router, albeit one with specific encapsulation requirements. By applying standard firewall policies to these tunnel interfaces, you retain the ability to apply the same security rigor to encrypted traffic that you apply to traffic originating from your local physical ports. You should never assume that because traffic is coming from a VPN tunnel, it is inherently trusted, as the tunnel simply provides a way to transport insecure data across a public medium. By enforcing strict security policies at the tunnel ingress and egress points, you minimize the blast radius if the remote location is ever compromised. This integration of VPN architecture into the wider firewall routing and security policy fabric is what ultimately makes the Palo Alto Networks platform a coherent system, rather than a collection of disparate features. See you in the next lecture. Welcome back. Let us explore the structural requirements for establishing secure remote access using GlobalProtect. This chapter focuses on the architectural design and deployment steps necessary to extend your corporate perimeter to a distributed workforce. To begin deployment, we must understand that the GlobalProtect framework is composed of two primary logical roles: the portal and the gateway. The portal acts as the control plane for the remote infrastructure, managing authentication, distributing client configurations, and directing users to the appropriate gateways. The gateway, conversely, serves as the data plane, responsible for terminating IPsec or SSL VPN tunnels and enforcing security policies for the authenticated traffic. From an interface perspective, you should configure these roles on distinct or shared physical interfaces depending on your security zoning requirements. It is a common professional practice to isolate the external interface dedicated to VPN traffic from other internet-facing services to simplify security zone management. Each interface hosting these services must have an appropriate management profile enabled to allow for necessary protocol responses, such as HTTPS for portal access. By separating the logical roles from the physical interfaces, you gain granularity in how you apply security policies to the incoming remote traffic. Certificate management is the cornerstone of a secure GlobalProtect deployment because the integrity of the tunnel relies on trust. You need to ensure that the firewall possesses a valid certificate for the identity of the portal and gateway, which should be issued by a trusted internal or public certificate authority. When the GlobalProtect client initiates a connection, it will validate whether the server certificate presented is signed by a CA it trusts, preventing man-in-the-middle attacks. Therefore, you must propagate the root CA certificate to all managed endpoints before you launch the remote access solution. For unmanaged assets, you might consider using publicly trusted certificates to avoid the complexities of internal root certificate deployment across heterogeneous device environments. Always remember that the common name or subject alternative name in the certificate must match the fully qualified domain name that the user's client resolves to access the portal. Failing to align these identifiers will inevitably result in connection errors and user support friction. The configuration of the portal address and the associated client download management paths are critical for the initial onboarding process. When you define the portal configuration, you are essentially telling the client which resources are available and how it should behave during the pre-logon or post-logon stages. You have the ability to host the GlobalProtect agent software directly on the firewall, or preferably point users to a repository where they can download the package for their respective operating systems. Managing these paths effectively ensures that users stay updated with the latest agent version, which is vital for maintaining security features like host information profile gathering. When a client first attempts to connect, it queries the portal, receives the agent configuration, and identifies which gateway is closest or designated for its specific user group. This orchestration happens seamlessly provided that your resource allocation mapping correctly correlates user identity definitions with the assigned gateway addresses. Resource allocation mapping allows administrators to define what internal network segments or applications are reachable once the tunnel is established. You implement this by defining split tunneling or full tunneling logic within the client configuration settings of the portal. In a split tunneling scenario, you explicitly identify the internal subnets that should be routed through the VPN tunnel, while leaving general internet traffic to use the client's local connection. This design choice significantly reduces the bandwidth consumption on your centralized firewall, which is particularly beneficial for distributed workforce models. However, if your security policy demands full inspection of all traffic, a full tunneling approach forces every packet through the gateway, ensuring that all security profiles like threat prevention and URL filtering are applied consistently. When planning this, you must balance the overhead of encrypted transit against the security requirements of your specific compliance framework. We will continue our discussion of the VPN framework in the next part of the course. See you in the next lecture. Welcome back. In this lecture, we are going to dive into the GlobalProtect portal, which serves as the central administrative hub for managing the behavior of your remote access architecture. When we talk about the GlobalProtect portal, we are essentially defining the control plane for the entire remote access deployment. Unlike the gateway, which handles the actual tunnel and traffic enforcement, the portal acts as the source of truth for the client. Think of the portal as the configuration broker that dictates which settings, certificates, and gateways a client should receive based on their identity and network context. You must configure an authentication profile on the portal, which validates the user before they are ever allowed to download the client's software or configuration. Whether you're using LDAP, Radius, or a modern SAML provider, this authentication layer is non-negotiable for maintaining a secure security posture against unauthorized entry attempts. Once the user is authenticated, the portal parses the client configuration selection criteria to determine which set of policies matches the user or the machine. This is where you begin to see the power of dynamic policy assignment, rather than relying on stale, static configurations. The network configuration section within the portal is where you define the operational parameters that the client agent will adopt upon successful connection. This includes the list of accessible gateways, the tunnel settings, and the specific interfaces the agent should use to establish connectivity. It is a common design pattern to present multiple gateways to the client, allowing the GlobalProtect agent to perform health checks and automatically connect to the most responsive node. By setting up backup portal configurations, you ensure high resiliency for your mobile workforce, providing a failover mechanism if the primary portal becomes unreachable during an outage or maintenance window. These configurations are packaged into an XML file that the agent downloads, effectively updating the client's local logic without requiring manual intervention from the end user. Managing this flow correctly is critical because a misconfigured portal will prevent the agent from even discovering the gateways, effectively breaking the remote access path before it starts. We also need to consider the nuances of agent behavior and login lifetime settings, which often dictate how transparent or intrusive the user experience becomes. You can define the connection methodology, such as pre-logon, which establishes a secure tunnel before the user has even provided Windows or macOS credentials. This is vital for scenarios where machine-based policies must be enforced regardless of the user logged into the console. The login lifetime rule defines how long an authentication session remains valid, directly impacting how frequently a remote user is prompted for credentials or secondary multi-factor authentication. Fine-tuning these values requires a careful balance between user friction and the security requirements of your organization. When you configure the app settings for the agent, you are dictating visibility, such as whether the user can modify their connection settings or if the agent should operate in a transparent, hidden background mode. The interaction between the portal and the agent is an iterative process that relies on a specific sequence of operations. The agent first reaches out to the portal to retrieve the configuration, which includes the list of gateways and the necessary certificates required to establish trust. Once trust is established via these signed certificates, the agent begins the transition from the provisioning phase to the steady-state connectivity phase. During the configuration selection process, the order of rules in the portal settings is critical, as they are processed in a top-down fashion. If a user matches the initial criteria defined in your configuration list, the agent receives that specific set of instructions and stops further parsing. This allows for granular control where different groups, such as contractors versus full-time employees, receive different gateway assignments and access levels seamlessly based on their authenticated credentials. See you in the next lecture. Welcome back. In this lecture, we shift our focus to the configuration of a GlobalProtect gateway, which acts as the termination point for secure user tunnels. To begin configuring a GlobalProtect gateway, you must first navigate to the Network tab and select the GlobalProtect Gateways menu within your firewall configuration. The initial step involves defining the general settings, where you bind the gateway to a specific interface and specify an IP address. Since the gateway terminates tunnels, it is essential to select a certificate from your trusted store to ensure valid SSL/TLS handshakes for incoming client connections. Once the interface and certificate are aligned, you will define the authentication profile, which dictates how remote users verify their identity against your configured user ID sources. It is important to note that the authentication profile here should align with your broader security strategy to ensure consistent identity propagation across the network infrastructure. Without a correctly mapped interface and a trusted certificate, the gateway will fail to initiate the cryptographic handshake required for establishing the connection. After the initial setup, you must address the tunnel interface settings, which facilitate the actual routing of decrypted traffic into the internal network. You will assign a specific tunnel interface to the gateway and define the IP pool from which remote clients receive their internal addresses. It is advisable to use a dedicated subnet for these pools to avoid overlapping with internal segments, which would otherwise lead to routing instabilities and connectivity issues for the end users. Furthermore, you will configure the client settings, where you establish the DNS server reachability and domain suffix information that the client adapter adopts upon connecting. By correctly defining these network parameters, you ensure that the remote endpoint behaves as though it were physically located inside the corporate network, maintaining the same access patterns and security expectations as an office-bound resource. Split tunneling is a critical component of the gateway configuration because it allows you to optimize bandwidth consumption by deciding which traffic enters the tunnel and which remains local. You can configure split tunneling based on domain names or specific application traffic, which is vital for preventing scenarios where latency-sensitive traffic like voice or video congests your enterprise backbone. Ideally, you want to route only corporate traffic through the gateway while allowing public internet traffic, such as streaming services or software updates, to exit through the client's local broadband provider. This requires a meticulous approach to defining the access routes, as an overly restrictive policy can break reachability, whereas an overly permissive one can introduce unnecessary load on your throughput capacity. Careful alignment of these routes remains one of the most effective ways to balance security posture with a seamless end-user experience. Finally, you must consider the operational limits of the gateway by configuring the appropriate timers and network boundaries to prevent session exhaustion. Setting realistic inactivity timeouts and maximum connection durations is a standard practice for maintaining the integrity and availability of your VPN infrastructure. By monitoring the threat logs once these parameters are active, you can observe whether your chosen timeout values are causing premature disconnections or allowing stale sessions to persist for too long. Alongside these settings, ensure that your cryptographic profiles are locked down to only support modern, strong ciphers to maintain a high security tier as per your zero trust requirements. Proper maintenance of these boundaries prevents resource saturation and keeps the firewall memory utilization within healthy bounds over long periods of operation. The culmination of these steps builds a robust environment that safely transitions remote workers into your enterprise ecosystem. I look forward to our next session together. Welcome back to our discussion on securing remote endpoints through the GlobalProtect architecture. Today, we explore host information profile or HIP enforcements to ensure that only compliant devices access our corporate resources. When we allow users to connect to private resources from outside the perimeter, we implicitly expand our attack surface to include their personal or managed machines. We cannot blindly trust an endpoint simply because the user possesses valid authentication credentials. The HIP subsystem allows the firewall to act as a gatekeeper, verifying the posture of an endpoint before granting access to sensitive internal segments. By utilizing the Global Protect application, the firewall essentially requests a hardware and software manifest from the remote client. This manifest acts as a health check, confirming that the device meets the security standards defined by your organization's compliance policy. The data collection performed by the Global Protect agent is comprehensive, covering core aspects of the host operating system. It gathers details regarding the installed patch levels, which is critical for mitigating vulnerabilities associated with outdated software. Furthermore, it inspects anti-malware versions and their definition update status to ensure proactive threat detection. Disk encryption status, such as BitLocker or FileVault, is also captured to enforce data at rest protection. Even specific registry keys or file hashes can be queried, allowing security administrators to verify the existence of enterprise-approved software or security configurations. Constructing a HIP object involves defining the criteria that constitute a compliant or non-compliant device. You might choose to create separate objects for OS versions, specific encryption states, or the presence of a required endpoint agent. Once these individual data points are defined, you aggregate them into a single, cohesive HIP profile. This profile acts as a logical construct that can be applied directly to a security rule within your policy base. When the firewall performs a rule lookup, it evaluates both the source user identity and the associated HIP status of that user's current session. Configuring this enforcement requires a strict approach to policy design, where you balance security requirements with operational usability. You must explicitly reference the HIP profile within the security policy settings under the Source tab. If a device fails to meet the criteria defined in the profile, the traffic match will fail against that specific rule. This allows you to implement a granular access control strategy, such as denying access to sensitive databases from unencrypted machines while still allowing internet access. It is paramount that your policy is ordered correctly, as standard top-down processing applies to these evaluations just as it does with any other firewall policy match. Effective enforcement relies on proper configuration within the GlobalProtect portal and gateway. The portal must be configured to inform the client which data points to report, and the frequency of these updates should be tuned to balance performance against visibility. Frequent updates provide tighter security, but increase bandwidth consumption on the remote link. You must also account for scenarios where a device might be considered compliant in one network segment, but not another, depending on its specific role or usage. Regular monitoring of the HIP logs is necessary to tune your profiles and avoid blocking legitimate users who may still be in the process of applying updates. By implementing these checks, you transition from traditional perimeter-based security toward a more robust, identity-aware, and device-aware model. This approach minimizes the risk of compromised or neglected devices, serving as an entry point for lateral movement within your network. While the initial setup of these profiles across heterogeneous client environments can be complex, the visibility gained is invaluable for maintaining security hygiene. You are now equipped to define standard security postures and enforce them programmatically at the point of ingestion. This creates a predictable and defensible posture for your mobile workforce, regardless of their geographical location or network origin. We will continue our exploration of VPN design in the upcoming lecture. Welcome back to our exploration of Palo Alto network security, where we now turn our attention to the resilient design of enterprise VPN architectures. In this lesson, we will dissect the mechanisms required to achieve high availability across distributed gateway environments. Achieving true redundancy in a GlobalProtect environment requires moving beyond simple primary-secondary failover models toward a more dynamic, multi-gateway architecture. When we talk about eliminating single points of failure, we are essentially building a system where the loss of a physical security appliance or an entire data center does not terminate the connectivity of the remote workforce. The foundational approach here involves publishing multiple gateways within the GlobalProtect configuration, which allows the client software to perform a selection process based on availability, latency, or predefined priority. If a primary gateway becomes unreachable, the client proactively attempts to establish an IPsec tunnel with the next available gateway in the hierarchy. This process is seamless to the user, provided that the session synchronization and authentication states are consistently maintained across the different geographic nodes. To make these gateways truly aware of the underlying network state, we rely heavily on dynamic routing protocols, rather than static routes that often fail to adapt to changing topology. Configuring OSPF or BGP over IPsec tunnels is a standard practice for enterprise engineers, as it transforms the VPN tunnels into active participants in the routing table. By advertising specific subnets through these tunnels, the Palo Alto firewall can dynamically adjust its routing preferences if a path becomes unavailable. Dead peer detection, or DPD, serves as our primary mechanism for detecting link failure at the tunnel level, ensuring that the control plane does not continue to attempt traffic delivery across a dead pipe. When DPD thresholds are reached, the SA association is torn down, triggering the routing protocol to withdraw the route and reconverge on an alternative path. Managing path selection becomes significantly more complex when we involve unequal cost paths or scenarios where we wish to utilize multiple tunnels simultaneously. We can manipulate the path preference by adjusting administrative distances or BGP attributes, which allows us to influence traffic flow based on throughput requirements or link costs. For scenarios where we have multiple equivalent paths to a remote destination, equal cost multipath, or ECMP, allows the firewall to load balance sessions across multiple VPN tunnels. Because GlobalProtect relies on encrypted tunnel interfaces, it is critical that we account for anti-replay windows and packet reordering when distributing traffic across ECMP member interfaces. Careful tuning of these parameters prevents the unnecessary packet drops that often plague unoptimized VPN load balancing setups. Ensuring that remote users experience a smooth transition during a failover event also requires an understanding of how gateway priority influences the selection algorithm. By assigning priority values to gateways, we can guide the client software to prefer a low latency path while keeping a standby path ready for instantaneous activation. If the preferred gateway experiences a failure during an active session, the client can initiate a tunnel restart and re-establish its connection to the redundant peer. We must ensure that authentication cookies or certificate-based trust remains valid across all redundant endpoints. Otherwise, the user will be prompted for re-authentication, which negates the goal of a seamless failover experience. This holistic view of the VPN infrastructure shifts the focus from managing individual tunnels to maintaining a reliable path state for the entire organization. I look forward to our next discussion on high availability configurations. Welcome back. In this chapter, we will examine the principles of Palo Alto Network's high availability architecture to ensure your network remains resilient against hardware and link failures. Building a robust high availability architecture starts with understanding how two physical firewalls synchronize their states to act as a single, cohesive security unit. At the heart of this design are the HA1 and HA2 ports, which serve distinct and vital functions within the cluster. The HA1 control link is responsible for the exchange of heartbeats, session synchronization, and configuration updates between the active and passive devices. It is crucial to treat this link as part of the control plane, meaning it requires reliable, low-latency connectivity to prevent false positives and failover detection. Meanwhile, the HA2 data plane link handles the direct synchronization of session information, ensuring that if a failover occurs, the new active device already possesses the necessary context to continue processing traffic without dropping existing connections. Because these links are mission-critical, industry best practices dictate the use of direct physical cabling or dedicated isolated Layer 2 paths, avoiding shared network infrastructure whenever possible. Effective HA deployments rely on a structured approach to interface management, particularly regarding the concept of backup links. While the primary HA1 and HA2 connections provide the baseline for synchronization, Adding backup links introduces the redundancy required to mitigate the risk of a single point of failure within the cabling or switch fabric. These backup connections are configured to take over immediately if the primary heartbeat signal is lost, thus preventing the dreaded split brain scenario. Split brain occurs when both firewalls believe the other has failed and simultaneously attempt to command the network, which can lead to traffic instability and security policy conflicts. To manage these risks, PAN-OS employs specific timers known as hello intervals and heartbeat thresholds that define exactly how long a peer is allowed to remain unresponsive before a failover is triggered. Careful tuning of these intervals is essential, as aggressive settings can prevent unnecessary failovers during minor network jitter, while excessively conservative settings might delay recovery during a genuine hardware outage. The mechanics of synchronization extend beyond heartbeat packets and touch upon how configuration mirroring keeps the firewalls in perfect lockstep. When you commit a configuration change on the active device, the system automatically pushes that update through the control plane to the passive unit, ensuring that both devices operate under the same security posture. This process is synchronized to maintain statefulness, meaning that the session table, the address object database, and the decryption cache are constantly shared. If one firewall stops receiving traffic, the transition process known as a preemption or failover event must happen essentially instantaneously. By implementing these architectural foundations correctly, you enable a seamless transition that is often completely transparent to the users on the network. As you design these environments, always consider the physical distribution of your links and the potential for electrical or physical surges to affect both devices simultaneously, favoring diverse paths whenever possible. See you in the next lecture. Hello, and welcome back to our deep dive into the Palo Alto Network's high availability features. Today, we are focusing on the mechanics of the active-passive HA configuration. In an active-passive deployment, we designate one firewall as the primary active unit and the other as a standby unit. The key to effective implementation lies in understanding state synchronization, where the active device constantly transmits session information, configuration changes, and ARP tables to the passive peer. This ensures that when a failure occurs, the standby unit is already equipped with the necessary stateful information to take over traffic forwarding with minimal disruption. You must configure the HA interfaces, specifically HA1 for control plane synchronization and heartbeat messaging, and HA2 for data plane synchronization, which includes session tables and IPsec security associations. While the HA control link can be established over a standard network, the data link is often best served by a dedicated direct connection to handle the high throughput of state information. Always ensure that the physical connectivity for these interfaces matches your intended design to avoid split brain scenarios where both devices incorrectly assume they are the primary owner of the traffic. Device priority parameters play a critical role in determining which unit assumes the functional role during a boot sequence or after a link failure. By adjusting these values, you can influence selection, keeping in mind that the unit with the lower numerical value is typically preferred as the active device. When we enable preemption, we allow a firewall that has been restored to service to reclaim its status as the active device, provided its priority is higher than the current occupant. Navigating the configuration menu, we must also define link and path monitoring groups, which act as the eyes and ears of the cluster's health. Link monitoring checks the physical status of specific interfaces, while path monitoring extends this by tracking the reachability of critical network resources beyond the firewall's immediate physical neighbors. If a monitored path fails, the firewall triggers a failover, ensuring that traffic is always routed through a path that provides genuine internet or data center access. Once the physical and logical parameters are set, you should routinely verify the health of your cluster using the command line interface. Commands such as show high availability state and show high availability group provide a granular view into the current mastership, peer connectivity status, and synchronization consistency. If you suspect heartbeat issues, checking the logs specifically for HA synchronization drift is a productive first step, as it often points toward mismatched software versions or interface misconfigurations. When conducting a software update, the clustered environment allows you to perform an upgrade on the passive member first, then initiate a graceful failover to make the updated unit active before finally updating the now passive partner. This methodology facilitates a near-zero downtime maintenance window, showcasing the robustness of the platform's stateful failover capabilities. Successful validation is achieved only when you can observe successful session seamlessness during a simulated hardware failure or a manual group switchover. See you in the next session. Welcome back to our exploration of high availability architectures and the specific challenges engineers face in complex enterprise environments. In active-active high availability, we are moving beyond simple redundancy into a design that requires both participants in a firewall cluster to actively process traffic. This configuration is purpose-built for asymmetric routing scenarios where return traffic might not traverse the same gateway that initiated the initial request. By deploying nodes in an active-active state, you provide the system with the capability to manage high-capacity throughput while ensuring that both firewalls remain state-aware. However, this architectural benefit introduces significant complexity, particularly regarding session ownership and the synchronization of flow information. You must ensure that the deployment accounts for the way these nodes communicate state and handle session setup across the dedicated high-availability paths. The foundation of active-active operations rests on the management of unique link groupings and the careful configuration of virtual MAC addresses. In this topology, each node acts as an independent routing entity for its own traffic, yet they work in concert to satisfy the requirements of the high availability pair. You will configure floating IP addresses that exist independently of the physical hardware, allowing for seamless transition and consistent gateway presence within the network topology. The virtual MAC address mapping is particularly critical as it allows upstream and downstream switches to maintain consistent ARP entries regardless of which node is currently processing the specific session. Without these strategies, the interconnected switching fabric would struggle to identify the correct next hop, leading to dropped packets and interrupted connections. Session ownership is perhaps the most nuanced aspect of the active-active configuration, as it determines which node holds the primary state information for a given flow. When a packet arrives at an interface, the system determines the session owner. If the packet arrives at the non-owner node, it must be forwarded through the HA3 control link to the owner node. This internal forwarding mechanism is essential for maintaining architectural integrity in asymmetric environments where traffic might arrive on different members of the pair. Engineers must design these HA3 links with sufficient bandwidth and low latency, as they become the backbone for session synchronization and cross-node communication. If the packet forwarding mechanism is misconfigured, or if the HA3 link becomes saturated, you will inevitably experience split-path application drops that are notoriously difficult to debug in a live network. Implementing this setup requires a disciplined approach to the packet forwarding mechanics and the underlying session establishment lifecycle. While active-passive designs simply shift state over to a standby node upon failure, active-active necessitates a synchronized pool of state information that is constantly updated across the cluster interconnect. You need to verify that your session setup triggers act consistently across both nodes to ensure that security policies are applied without variation regardless of the physical path taken. This approach demands a deep understanding of not just the Palo Alto hardware, but also the interaction between the firewall and your dynamic routing environment. By mastering these session mechanics, you ensure that the throughput capacity of your network is maximized without sacrificing the deep packet inspection capabilities that define a next-generation security deployment. I look forward to our next session. Welcome back. In this lesson, we will explore the Panorama centralized management architecture and how it scales security operations for distributed firewall environments. When we manage a single firewall, the cognitive load of maintaining security policies is minimal. But as an organization grows to include dozens or even hundreds of devices, individual management becomes unsustainable. Panorama serves as the centralized orchestration layer, decoupling the management plane from the data plane of our next-generation firewalls to provide a unified administrative interface. By consolidating security policies, device configurations, and log aggregation into a single pane of glass, we reduce the risk of configuration drift and simplify compliance reporting. Whether you choose to deploy Panorama as a dedicated physical appliance or as a virtual machine within your private or public cloud infrastructure, the functional objective remains the same, providing a consistent security posture across the entire estate. This architectural shift allows security teams to treat their network infrastructure as a fleet rather than a collection of isolated silos, which is essential for maintaining agility in modern, fast-paced enterprise environments. To bridge the gap between individual firewalls and the central platform, we must establish reliable inter-device connectivity. This communication is facilitated through specific protocols that ensure secure interaction between the managed firewalls and the Panorama management server. When a firewall is registered to Panorama, it initiates a connection using the management plane interface, typically directed to the Panorama management IP address over port 3978. It is vital to recognize that this communication path must be explicitly permitted through the network fabric, ensuring that the necessary traffic is not dropped by intermediate security controls. Beyond the initial path, we rely on mutual authentication to verify both sides of the relationship, preventing unauthorized devices from joining or masquerading within our management domain. This trust is anchored in SSL/TLS, where certificates serve as the gold standard for validating device identity during the secure handshake. Managing certificates effectively is a cornerstone of a robust Panorama deployment, as these assets underpin the security of all communication within the management fabric. During the onboarding process, the administrator must ensure that both the firewall and the Panorama server trust the necessary certificate authorities that sign these identities. We often use a hierarchical certificate structure where Panorama acts as an intermediate authority or resides as a client managed by an enterprise PKI, ensuring that identity chain verification succeeds every time a connection is established. Once the encrypted tunnel is active, the firewall registers itself, sending its serial number and platform type to the management server to initiate the heartbeat process. This configuration ensures that if a managed device goes offline or loses its connection to the management server, the administrative dashboard accurately reflects the state of the infrastructure in real time. The registration path is more than just a simple registration request. It often involves the utilization of serial numbers and the PAN-OS authorization codes to ensure that the license and feature set of the managed firewall are correctly inherited. Once a device has been successfully onboarded, it enters a state where it is ready to receive configuration updates, such as security policy rules and device-specific settings, pushed from the centralized server. This orchestration capability relies on a structured hierarchy of device groups and templates, which we will analyze in subsequent discussions to facilitate massive policy scalability. By maintaining a clean management architecture, we ensure that the communication between Panorama and its subordinates remains encrypted, authenticated, and resilient against network-level disruption. This centralized approach effectively transforms the way we observe and enforce security policies at scale, allowing for granular control while maintaining global visibility. I will see you in the next lecture. Welcome to this exploration of device groups and templates within the Panorama management ecosystem. This chapter will equip you with the structural knowledge required to govern large-scale firewall deployments through centralized configuration baselines. When we shift from managing individual firewalls to orchestrating an entire fleet, the concept of manual interface configuration becomes a structural liability. In a distributed environment, you want to move away from local device management and toward a model where configuration is treated as a reusable asset. Device groups serve as the organizational containers for your security policies, allowing you to define a hierarchy that dictates how rules are inherited across different organizational levels. By creating a parent-child relationship between groups, you can enforce global corporate security policies at the top tier while allowing subordinates to define their own region-specific rules. This tiered approach is the only way to manage a complex enterprise network without succumbing to the overhead of managing thousands of individual policy rules. The mechanics of policy evaluation in Panorama are rooted in the distinction between pre-rules, post-rules, and local rules. When a packet hits a firewall managed by Panorama, the security policy evaluation follows a strict order that prevents rule shadowing and ensures predictable outcomes. Pre-rules are defined at the top of the hierarchy and are evaluated first, which effectively locks them as mandatory security controls that local administrators cannot override. Post-rules sit at the bottom of the stack, providing a catch-all mechanism or a place for granular, lower-priority traffic filtering. Between these two sit the local device rules, which allow for a degree of flexibility that respects the global security architecture while accommodating local site requirements. Understanding this hierarchy allows an engineer to create a unified security posture that is simultaneously rigid enough for compliance and flexible enough for operational needs. While device groups manage the security and NAT policy intent, templates govern the underlying device architecture and networking definitions. A template is essentially a configuration file that contains the structural elements of the firewall, such as zones, interfaces, virtual routers, and management settings. Using a template allows you to define a standard for how your hardware connects to the network, such as standardizing loopback addresses, NTP servers, or routing protocols like BGP or OSPF. When you have varied hardware models across your network, you might worry that a single template might force invalid configurations onto a device. This is where template stacks come into play, as they allow you to aggregate multiple templates into a single logical deployment unit. Template stacks work by layering common configuration definitions on top of device-specific ones to create a complete, effective configuration. You can define a base template that applies standard DNS, logging profiles, and global settings to every firewall in your organization. You then attach a second template to the stack that contains the interface specifics or virtual router configurations unique to a particular site or hardware family. Because the stack processes these templates in order, the device receives a merged configuration set that adheres to both global standards and local site requirements. If you modify a value in the base template, that change propagates instantly across every firewall attached to the stack, significantly reducing the maintenance window for infrastructure updates. This modular approach is essential when managing heterogeneous environments where some sites might be using high-throughput data center appliances while others run smaller branch firewalls. The interaction between device groups and template stacks defines the modern paradigm for Palo Alto Networks infrastructure management. It is important to note that these two entities operate on different logical layers and are mapped together within the Panorama device deployment section. A firewall can be assigned to a specific device group for policy management and, independently, to a template stack for configuration management. This separation of concerns is a powerful architectural pattern that mirrors the best practices of clean code, where we isolate policy intent from structural implementation. By maintaining this decoupling, we gain the ability to migrate devices between groups or update network configurations without accidentally disrupting the security policy logic. Proficiency in this orchestration is exactly what distinguishes a professional-grade architect from an operator. I look forward to discussing how these structures support centralized visibility in the next lecture. Welcome to the chapter on centralized logging and analytics, where we explore how to gain visibility across your entire distributed firewall estate. We will focus on the architectural components required to aggregate, store, and analyze security data efficiently. In an enterprise environment, managing logs on a per-device basis is unsustainable. Panorama provides a centralized management plane, but for logging, we must implement collector groups to scale our ingestion capabilities. A collector group acts as a logical entity that pools the disk capacity of multiple log collectors, allowing for high availability and load balancing of log data coming from various firewalls. By grouping these resources, you ensure that even if one collector node fails, the ingress of traffic, threat, and system logs continues without data loss. When designing these groups, you should consider the geographical distribution of your firewalls to minimize latency, although the primary goal is ensuring that the storage capacity matches the log volume generated by your specific traffic throughput. To facilitate this flow, you must configure log forwarding profiles on the individual firewalls, which dictate which logs are sent to Panorama or external destinations. These profiles define the criteria for what is sent, such as specific threat levels or traffic patterns, effectively filtering noise before it consumes network bandwidth or storage. Within the log collector settings, you will define retention parameters, which are essentially the aging policies that dictate how long logs remain on disk before being purged or overwritten. This requires a calculated balance between your compliance requirements and the physical storage limits of your logging appliances. It is a common misconfiguration to set overly aggressive retention times without considering the long-term impact on your storage arrays, leading to premature data deletion when incident response teams might need historical context. Beyond simple storage, the strength of the Panorama architecture lies in its ability to aggregate diverse event types into a unified view. You can correlate traffic logs with threat logs and system-level events, providing a holistic view of the security posture rather than fragmented snapshots. Once this data is aggregated, you can leverage custom dashboards to visualize specific security metrics or anomalous behaviors tailored to your organization's unique threat landscape. These dashboards are not merely for monitoring. They serve as a powerful tool for generating compliance reports that document policy enforcement and incident resolution for stakeholders. By structuring your analytics, you transform raw data, which is often noisy and voluminous, into actionable intelligence that informs your ongoing security strategy and policy refinements. Enterprise visibility frequently extends beyond the Palo Alto Networks ecosystem, necessitating automated log forwarding to external SIEM platforms. Using protocols such as syslog or the dedicated Panorama API, you can stream security events directly into a centralized security operations center platform. When configuring these connections, ensure you are utilizing encrypted transport mechanisms where possible to maintain the integrity of the data in transit. You also have the flexibility to filter the forwarded logs specifically for the SIEM, ensuring that the external platform is not overwhelmed by purely informational traffic that lacks security value. Carefully managing this egress traffic prevents performance degradation on the Panorama management server while still providing the necessary telemetry for broader organizational security orchestration and incident management. See you in the next lecture. Welcome back. In this session, we will examine the mechanics of granular packet capture engines to effectively troubleshoot complex connectivity issues by isolating traffic at different stages of the firewall pipeline. When we approach packet inspection on a Palo Alto Networks firewall, we must first understand that traffic does not simply flow through a monolithic pipe, but rather traverses specific architectural stages. The packet capture engine allows us to intercept data at four distinct points: the receive stage, the firewall stage, the transmit stage, and the drop stage. The receive stage captures traffic immediately upon ingress before any complex processing or policy lookups have occurred. By isolating this stage, we can verify whether the raw frames are reaching the physical interface or arriving with expected VLAN tags. If your traffic is failing to ingress or exhibits signs of corruption at the Layer 2 level, this is the primary location to start your investigation. Moving beyond initial ingestion, the firewall stage captures packets after the firewall has processed headers and performed session lookups. This is crucial for verifying that the traffic has actually made it into the internal logic of the device for processing. The transmit stage is equally vital because it captures packets after they have passed through all security policy evaluations and routing decisions just before they leave the egress interface. If you find that packets are appearing in the receive stage but are mysteriously absent from the transmit stage, you have immediate evidence that the traffic is being intercepted by an internal mechanism. This leads us directly to the drop stage, which is perhaps the most significant diagnostic tool for complex connectivity issues. The drop stage specifically logs and captures packets that the firewall has decided to discard due to security policy enforcement, DOS protection triggers, or internal buffer errors. By configuring filters to specifically monitor the drop stage, we can view the associated drop codes that explain exactly why the packet was discarded. These codes are not mere suggestions. They are explicit indicators often pointing to issues like packet storms, policy violations, or malformed traffic signatures. A frequent point of confusion involves offloaded traffic, as the single-pass parallel processing architecture often utilizes the data plane's hardware acceleration to move packets quickly. When a session is successfully offloaded to the processing engine, it effectively bypasses the software-based inspection logic that standard packet captures rely upon to generate logs. To view this traffic, you must explicitly enable the capture of offloaded traffic, which instructs the data plane to mirror these sessions to the capture engine. Failure to do so will frequently result in empty capture files even when you know traffic is actively passing through the system, erroneously leading you to believe the traffic has ceased. Once you successfully collect your PCAP files, the native management plane interface is rarely the best place for detailed analysis. Instead, you should export these files to an external analyzer like Wireshark, where the granular protocol decoding and flow reconstruction tools are far more robust. When you open these captures in an external tool, focus specifically on the sequence numbers and the time deltas between packets. Often, connectivity issues that appear to be policy-related are actually timing issues, TCP retransmissions, or window size negotiations being crushed by mismatched MTU settings along the path. Using Wireshark, you can apply display filters to isolate specific streams and verify if the three-way handshake completes successfully or if the firewall is resetting the connection due to an asymmetric routing condition. Asymmetry is a classic diagnostic challenge where the request enters via one path and the return traffic attempts to exit or enter through an interface that the firewall does not associate with that session. By mapping the capture timestamps against your security logs, you can align the exact moment a packet was dropped with the corresponding entry in the traffic logs. This correlation is the fundamental prerequisite for solving network anomalies in a high-traffic environment without sacrificing the stability of your production services. See you in the next lecture. Welcome back to our technical journey through the Palo Alto Network's landscape. In this session, we will examine the session browser and various logging repositories to refine your diagnostic approach. When troubleshooting traffic that fails to traverse the firewall as expected, the session browser serves as your primary interactive window into the live state of the device. This tool allows us to query the active session table based on specific parameters such as source IP, destination IP, application, or service port. By isolating a specific flow, we can immediately identify the current state of a connection, which might be in a state of initialization, established, or perhaps stagnating in a closing phase. It provides a real-time snapshot of the traffic flow as it is currently being processed by the SP3 architecture. When you look at an entry in the session browser, you are essentially looking at the record that the firewall has created in memory to track a specific packet flow. If a connection is failing, the information here, such as whether the traffic matches the intended security policy or which NAT rule is being applied, is often the quickest indicator of a misconfiguration. It is important to note that the session browser is a reflection of current, active memory, and it does not store history, which is why it is often the first place to look when a user claims an application is currently unreachable. Beyond simply observing the state, the session browser provides the utility to perform session management, specifically the ability to manually clear hung sessions. This necessity arises when a session remains in the table despite the end host having terminated the connection, or when persistent connections become corrupted by state tracking anomalies. Clearing a session forces the firewall to drop its current state for that specific 5-tuple, effectively requiring the next packet to initiate a new session request. This is particularly useful in testing scenarios where you need to force reauthentication or ensure that a new security rule or policy change is applied to a flow that was previously matched. However, one must exercise caution here, as aggressively clearing sessions in a production environment can cause operational disruption. Using this tool effectively requires you to be systematic, ensuring that you are only targeting the suspect flow after you have verified that the traffic is indeed not reaching its intended destination or being handled incorrectly by the security policy. While the session browser gives us the present state, the log repositories allow us to perform the necessary forensic work after a connection has failed or been dropped. The traffic, threat, and system log databases are where we find the historical context of traffic events, including why a specific packet was blocked or which policy was triggered. Within the traffic log, checking the flags for session end reason is critical. Seeing a reason like TCP worst from client or policy deny helps narrow down the search space significantly. For instance, if you are suspecting a routing or NAT issue, the traffic logs can reveal the egress interface or the translated IP addresses, which might contradict your design expectations. The threat log is equally important, particularly when you are diagnosing why traffic passing through the firewall is being intercepted by a security profile. These logs provide the underlying evidence for why the firewall decided to behave in a specific way, acting as the definitive source of truth when the live session browser does not tell the full story. Integrating both tools requires a methodical workflow that balances real-time visibility with post-event analysis. I usually start by attempting to replicate the issue while monitoring the session browser to see if the packet arrives at the firewall ingress and gets matched to the correct zone. If the entry does not appear, your issue is likely routing or a physical layer concern before the traffic ever hits the firewall. If it appears but is immediately dropped or marked with a deny action, check the security policy rule name column to identify exactly which rule is responsible. Once you identify that, compare the matched rule parameters against your current policy set. Welcome back. In this lesson, we will focus on advanced diagnostic operations within the PAN-OS command line interface to isolate complex system-level constraints. The command line interface, or CLI, serves as the primary gateway for granular infrastructure debugging when the web management console reaches its visibility limits. While the graphical user interface provides an excellent overview of policy compliance and traffic patterns, it sometimes abstracts away the underlying state of system subsystems. Through the CLI, we can interact directly with the management server, known as the MGMGS daemon, and various internal processes responsible for app ID and user ID enforcement. Mastering these commands allows you to verify internal counterstates that represent synchronization issues between the data plane and the control plane. You should approach the CLI as a surgical tool, particularly when you need to confirm whether a user ID agent is correctly pushing mapping updates to the firewall or if the app ID pattern matcher is encountering unexpected latency. Every command you execute here provides a raw look at the system's runtime health, which is essential for diagnosing issues that do not manifest in high-level log filters. One of the most critical aspects of CLI-based diagnostics involves checking interface counters and daemon status to determine if hardware resources are under pressure. You can utilize commands like show system resources to monitor CPU and memory utilization per process, which is invaluable for identifying runaway daemons that might affect traffic throughput. When you suspect that a specific app ID process is misbehaving, querying the state of that subsystem through the CLI can reveal whether the detection engine is dropping packets due to resource exhaustion or internal memory buffer constraints. Furthermore, the CLI allows for the extraction of logs that are often stripped or transformed in the standardized reporting format, giving you a clearer picture of events as they occur in real time. By systematically querying the subsystem status, you move beyond merely observing that a problem exists and start understanding the specific mechanism responsible for the performance degradation. This level of visibility is what distinguishes a proficient engineer from a novice when resolving obscure firmware-related anomalies in high-traffic environments. Real-time packet diagnostics through the CLI act as a final layer of validation, especially when dealing with complex networking scenarios where standard flow logs offer insufficient detail. By utilizing debug-level commands, you can intercept traffic at various stages of the single-pass parallel processing pipeline to see how policies and profiles are applied to individual sessions. This allows you to differentiate between traffic that is dropped due to an explicit security rule and traffic that is discarded because of an internal processing error or hardware-level anomaly. Understanding how to interpret these CLI outputs requires a solid grasp of the firewall's internal architecture, as the data presented is presented in its most rudimentary, unformatted state. When you view these counters, look for discrepancies between ingress and egress packets, as these are frequently the first indicators of a configuration error or a faulty physical interface. Maintaining a methodical approach to these diagnostics ensures that you can isolate infrastructure constraints without inadvertently introducing further instability into the environment during the troubleshooting process. I will see you in the next lesson. Welcome back. In this session, we will examine the physical and logical health of Palo Alto Networks appliances to ensure operational stability. When we approach hardware and platform troubleshooting, we are essentially moving from the software-defined world of policy and routing into the realm of silicon and resource management. A Palo Alto Networks firewall is a specialized computer running PAN-OS, and like any complex computing system, it expects to operate within specific physical and logical parameters. You must first understand the distinction between the management plane, or MP, and the data plane, also known as the DP. The management plane handles control functions, management traffic, and configuration updates, while the data plane is dedicated to the high-throughput processing of sessions via the security processors. When you observe a performance issue, the first diagnostic step involves determining which of these planes is under duress. If the web interface is unresponsive but traffic continues to flow, you are looking at an MP bottleneck. Conversely, if traffic latency spikes while the CLI remains snappy, the DP is likely saturated by heavy traffic loads or an inefficient security policy configuration. Monitoring these two planes independently is a prerequisite for any meaningful investigation. CPU utilization is often the first metric engineers inspect, but it can be deceptive without context. Seeing a 90% CPU utilization on the data plane is often normal behavior for a high-traffic firewall, provided that the system is successfully processing packets. However, if that high utilization is coupled with dropped packets or a slowdown in new session establishments, you have a genuine strain on resources. When you investigate these spikes, you should use the CLI command to view system resource monitoring, which displays historical graphs of CPU and memory. A persistent, creeping increase in memory utilization, particularly on the management plane, often points toward a memory leak or an accumulation of unmanaged process states. You must differentiate between expected caching behavior and genuine resource depletion. If your memory usage climbs steadily until a process crash occurs, you need to begin looking at the specific services running on the management plane. This usually involves inspecting logs or generating a tech support file to capture the state of the processes at the time of the incident. Disk storage is another common failure point that is often overlooked until it becomes a catastrophic error. Every appliance has finite space for logs, local reports, and system images. And if the log partition reaches its quota, the firewall will stop recording data. This is a critical failure because you lose the audit trail necessary to debug any other issues that might be occurring concurrently. You should regularly check the log storage quota and ensure that log forwarding is correctly configured to an external destination, like Panorama or an external syslog server. Beyond logs, environmental status metrics provide an early warning system for physical hardware degradation. Sensors within the chassis monitor fan speed, power supply voltage, and internal temperatures. These values should be within the manufacturer's specified thresholds. An appliance operating in a hot environment with obstructed airflow will eventually throttle its CPUs to protect the silicon, leading to the exact performance degradation you are trying to solve. If an appliance reaches an irrecoverable state, you must have a clear path to restoration. The tech support file is the ultimate source of truth when working with support, but you should also be comfortable with the system's recovery modes. If a software update fails or the boot partition becomes corrupted, booting the firewall into maintenance mode allows you to re-image the system or perform a factory reset. This is the last resort, intended for situations where the standard configuration management tools are inaccessible. Even in these high-pressure scenarios, your approach should remain methodical. Use the system's built-in diagnostics to isolate the fault to a specific subsystem before taking destructive actions. By understanding the interaction between the physical hardware and the PAN-OS processes, you minimize downtime and ensure the integrity of your security posture. I will see you in the next lecture. Welcome to our discussion on exam strategy, where we will refine your approach to the PSE Strata System Engineer Professional Certification. By the end of this session, you will possess a tactical framework for navigating the blueprint and optimizing your performance on the actual exam. To master this certification, you must first align your study efforts with the weighted distribution defined by Palo Alto Networks. The blueprint is not merely a list of topics, but a strategic map that highlights exactly where the exam places its emphasis, such as firewall architecture, identity technologies, and threat prevention. By prioritizing high-weight areas, you ensure that your preparation time yields the highest return on investment. Do not treat every domain as equal, because the reality of the test is that certain core concepts, like the single-pass parallel processing engine, form the bedrock of almost every architectural scenario you will encounter. You should spend a significant portion of your time understanding how these subsystems interact under pressure, as the exam rarely tests isolated, theoretical definitions. Instead, it expects you to synthesize knowledge across multiple security domains to solve complex operational challenges. Start your preparation by cataloging the blueprint categories and cross-referencing them against your current depth of understanding to identify your weakest links. The exam is notorious for its situational analysis questions, which require you to move beyond rote memorization and apply logic to real-world network failures. When faced with a scenario-based architecture challenge, your primary goal is to isolate the specific technical constraint or requirement being presented by the prompt. Many candidates lose marks by rushing to the options before identifying the key variables, such as specific deployment modes or latency requirements that rule out certain configurations. Practice the disciplined habit of reading the final sentence of each scenario first, as this often reveals the exact metric or objective. like throughput or segment isolation, that the test designer is concerned about. Once you have identified the goal, systematically eliminate options that violate basic security principles or the fundamental constraints of the specific Palo Alto platform architecture. By narrowing down the potential answers using a process of logical deduction, you significantly increase your probability of selecting the correct path even when faced with ambiguous choices. Multi-select engineering items represent a unique hurdle because they remove the safety net of choosing a single best answer. In these instances, you must evaluate each provided option as if it were a Boolean true or false statement, carefully checking for qualifiers like specific interface requirements or prerequisite policies that might make a potentially correct technical choice invalid in that specific context. Focus on the dependencies between features, such as how user ID mapping dictates the applicability of certain security policies, to verify that your selected combination of answers achieves a cohesive security posture. If the question asks for a comprehensive solution, ensure that your chosen combination addresses all stated requirements without introducing unnecessary complexity or performance overhead that would contradict the professional standard. You should approach these items with the same rigor you would apply to a production change request, where every included component must be justified by the requirements of the scenario. Time management is critical here, so do not get bogged down in deep technical debates with yourself. If the evidence is insufficient to justify a component, exclude it and focus on the most architecturally sound options that remain. Successfully interpreting network diagrams is a core skill for the modern security engineer and a frequent task during this exam. When a diagram is provided, refrain from scanning it aimlessly and instead perform a structured decomposition of the topology. Look immediately for the trust zones, the placement of the decryption broker, and any routing markers that indicate asymmetric traffic flows or interface configurations. The exam often hides the answer in the nuances of these visual representations, such as an incorrectly configured tunnel interface or a missing security zone assignment that prevents traffic flow. Mentally trace the traffic path as if you were the packet moving through the firewall, checking against the expected policy actions and the active-passive or active-active high availability status. If you find yourself overwhelmed by the complexity of the diagram, zoom in on the specific interfaces in question and cross-reference them with the provided background information to filter out irrelevant noise. By maintaining this systematic approach, you prevent the visual density of the diagram from clouding your technical judgment. Effective study routines involve moving beyond passive reading and engaging with the concepts through active synthesis and simulated problem solving. Structure your remaining review time to build a mental model of the entire security lifecycle, from the initial ingestion of traffic to the final logging and reporting stages. Prioritize your final prep sessions on the areas where you struggle to explain the why behind a configuration change, as the exam questions often probe the reasoning behind why an engineer would choose one solution over another. Manage your exam timing by setting a strict pace, ensuring that you do not spend more than a set number of minutes per difficult item, which preserves capacity for the final questions in the session. Use the platform's internal documentation as a final authority during your review, as it provides the most precise definitions of feature capabilities and platform limitations. By continuously refining your cognitive framework and practicing the discipline of elimination, you will enter the testing room with the necessary composure to handle even the most intricate technical inquiries. I look forward to our next deep dive into these concepts. Welcome back to this final summary session of our Strata Engineer preparation. We will now consolidate our understanding of the enterprise security fabric before you approach the certification examination. In this concluding lecture, we are looking back at the architectural pillars that form the backbone of the Palo Alto Networks ecosystem. Throughout our time together, we have analyzed how the single-pass parallel processing engine provides the foundation for consistent security enforcement without sacrificing throughput. We examined how App ID moves beyond simple port-based filtering by identifying applications based on their unique signatures, headers, and behavior. This identity-aware approach is further enhanced by User ID, which ties network activity directly to human identities rather than transient IP addresses. By integrating these components with SSL decryption, we ensure that even encrypted traffic cannot be used as a shroud for malicious payloads to bypass our security controls. Each of these technologies was designed to work in synergy, ensuring that your security policies reflect business logic rather than network topology constraints. The orchestration of these security components is largely abstracted and managed through Panorama, which provides the necessary visibility and control for modern distributed enterprises. We discussed how device groups and templates allow an engineer to maintain structural consistency across hundreds of firewalls, while still allowing for site-specific customization. This centralization is critical, not just for policy deployment, but for the telemetry gathered through centralized logging and reporting. When you transition from a single firewall mindset to an enterprise strategy, you shift your focus towards scalability and operational efficiency. The goal is to minimize the management overhead of the security fabric while simultaneously tightening the zero-trust posture across all segments of the digital infrastructure. High availability, whether through active-passive or active-active configurations, ensures that this central intelligence remains accessible even during hardware failures. As you prepare to sit for your exam, remember that the most effective way to view the Strata platform is as a unified stream of data processing. When a packet enters the interface, it passes through the stages of flow lookup, app ID classification, user mapping, and policy evaluation before hitting the threat prevention engine. Any omission in one of these areas creates a blind spot that could potentially be exploited in a production environment. Your role as an engineer is to ensure that these subsystems, from URL filtering to wildfire, are tuned to work in harmony. Maintenance of this infrastructure requires proactive monitoring using the session browser and command line interface to detect anomalies before they result in a service outage or a breach. A strong engineer does not just configure a device. They understand how the state tables and packet buffers respond to traffic under load. The distinction between a standard firewall deployment and a hardened Strata implementation often lies in the details of the policy structure and decryption exclusions. Always prioritize the principle of least privilege, ensuring that every security policy rule is as granular as possible while remaining manageable. We reviewed how to audit these policies regularly to remove shadow rules and ensure that our application defaults are not overly permissive. Furthermore, your competency in troubleshooting via packet captures and logs will often determine how quickly you can restore service during high-pressure events. These diagnostic tools are not merely for debugging. They are primary instruments for verifying that your security design behaves as intended. Carrying this technical depth into the exam will prove far more effective than rote memorization of interface names or obscure menu paths. I trust that this review has effectively anchored the essential concepts we have explored throughout our sessions together. Please ensure you remain focused on the core integration points as you move toward your forthcoming certification milestones. See you in the next lecture.